Hi, this is John Carter. Welcome to the Sunrise Observatory in Paulden, Arizona. For the next 3.5 hours, I'm going to be demonstrating a little bit about my observatory and how I do astronomy, some of my equipment, and most importantly, looking at the Saturn-Jupiter conjunction that happened on December 21st, 2020. So sit down, relax, grab a big cup of coffee, and enjoy the show. On December 21st, 2020, Saturn and Jupiter came the closest together than they had been since 1623. The visual separation between the two planets was 0.1 degree, or 1/5 the width of the Moon. Although they form a conjunction, which is a close approach, about every 20 years, the next time they get within 0.2 degrees will be in 2080, and again in 2417. An actual occultation, where Jupiter hides Saturn, won't happen again until June 17, 7541.
So what you're looking at right now is the application that I'm using to actually monitor and control what my telescope is doing. So this green blob in the middle, that's the daytime sky. And that little white particle in the middle of that is Jupiter. So the center of the screen would be right about here. So Jupiter has drifted away that much in the past 20 minutes. So momentarily, I'll be getting it back into center. And we should see Saturn popping up right about there. So there's a tiny little white dot that I can see that you might not be able to see. If you were to go outside and look, you might be able to see the two planets side by side. They're only 0.1 degree apart at this point in time. So 0.1 degree, if you look at your little finger at arm's length is about 1 degree wide. So 1/10 the width of your little finger is what the spacing is right now between Saturn and Jupiter. So if I hold my fist up and with my closed fist across my knuckles, that's about 4 to 5 degrees, depending upon the size of your hand. So we use our hand as measurements. My thumb is about 1.5 degrees, almost 2 degrees. My index finger is a little over 1 degree. My little finger is 1 degree. I've already been calculated and got that all figured out. So the moon is only 1/2 of a degree. Now, to give you an idea of the size of space that we're looking at here, from top to bottom, that's just a little under 1/2 a degree. So if I were to look at the moon right now, it would fill up this area. So that'll give you an idea of how much far apart Saturn is from Jupiter. Saturn, I believe, is that little dot right there that I see on my screen, and Jupiter is there. I can adjust the exposure on my camera, but as I do that, then this area becomes whiter and whiter, and it washes out whatever we're looking at. So right now, the exposure time that we're looking at is 0.03 seconds. So just to give you an idea of what happens if I increase that, I had it on loop mode. So I'm going to increase that to 0.4, and you'll get an idea of what's happening. Turn the loop off. So I'm starting it, and down here, you'll see that it's exposing. Now it's debayering, stretching the image. Everything got a little brighter. So we can see, I can see now a little bit more right there. I'm going to turn off the crosshairs so that we can see what's going on. So right there, I see a little white blob on my screen, and you might not see it on your screen, but if you were to turn all the lights out in your room right now, then what you see here will show up a little better as far as the contrast is concerned. Okay, so there's another control that I can adjust for making things pop out a little bit more. Now, this diagram that you see over here is what we call a histogram, and it's telling me that all of this area right here is lit up, and down here there's no light, and over here there's no light. This is the black area, this is the white area. So this is pretty much what I would like to see if I was going for what we call a flat. In astrophotography, we have to take several different kinds of images and combine them together in order to get anything worthwhile. I'm going to zoom in on this a little bit and see if I can't get a little better image of everything. So now we're starting to see Saturn a little bit better here. Now, we're never going to see any really good detail in Jupiter. And that's because it needs to be really dark out, and I need to have a really high magnification going. And I can't get the kind of magnification with this particular computer in order to see that, at least not with the configuration that I've got it right now. And the other thing that's required in order to see the detail of a planet would be a camera that has extremely small pixels in it. So the pixel size in the camera that I'm using right now is quite large by comparison. So we need something that's in the order of 2 or 3 pixels or 2 or 3 microns for a good planetary camera. But the pixel size that I've got in this camera is closer to 6 microns, so it's pretty heavy. But there's lots of them. It's a 24 megapixel camera, so it's super high resolution in that regard. It's also a one-shot color camera. So a one-shot color camera simply means when I take a picture of something, I get red, green, and blue all together, and there's going to be 2 green for every 1 red and 1 blue pixel. So think about that. If you put them together, you got 4 dots. Actually, it's a combination of 4 dots when you look at the mosaic. 2 of them are going to be green, 1 red, 1 blue. So we get twice as many green images as we do red and blue images, and that's why we're probably looking at a green screen here. But there are ways of adjusting those colors so that what you wind up with is something that looks more natural to the eye. And that's what this control up here attempts to do. So when I click on that control, it attempts to adjust the red, green, and blue so that we get more of a natural looking color. And that's why it now looks gray instead of green. So that's a little history there on astronomy. So as I move this back and forth, you can actually see that Saturn, which is right here, as it moves across, it gives you an idea. Now, as it gets darker and darker, so somewhere around 6:15, we will have, it'll be dark enough, actually maybe even by 6 o'clock, it'll be dark enough to see the ring of Saturn. But in order to see Saturn's ring, I have to have a lower exposure for, a higher exposure for Saturn, and that will blow out Jupiter completely. And also in order to see the moons, we're going to see a string of moons across here as the sun sets. Now, Jupiter only has 4 moons that we can actually see, typically. And last night when I was looking at Jupiter, it appeared that there was a 5th moon in there someplace. And I couldn't believe my eyes when I saw that. And somebody else saw the same thing. But I think that 5th moon is actually a star that's happened to be in line with the moons. So we'll see that as the sky gets dark. And we have a pretty bright sky right now, 10 minutes after 5. Now, what I'm going to be showing you later on tonight, after about 6:20, right about that time, if you'll notice, I probably have some pictures that I can show you of my astronomy, my observatory. That would be nice to give you an idea of what's going on here. Let me see if I can bring it up real quick. And I'm just doing a search in my photos library. You're still looking at, you're looking at the photo library too. Okay. So right here, that's a picture of my observatory. It's 10 inches or 10 feet wide and 12 feet long. And it's a regular shed that I bought, a metal shed. And I had to cut a door opening here and add a door to it. Now this roof literally rolls off in that direction. So when it's open, then my telescope sticks up out of the top of it, but it's not 100%. I really can't level my telescope with the ground, because if I level it with the ground, then it's going to be looking literally into the wall of the observatory. So I can't see literally the sky other than about 15 degrees. Anything below 15 degrees, I won't be able to see that. Now you'll over to here, this little area thing sticking out here is the corner of my garage. And it's actually sticking up higher than my observatory is. But if you'll notice the apex of this roof right here, as I slide that back, it's going to prevent me from seeing to the west by that amount. So my telescope is centered right in here. And this is facing due east and west and due north and south in this direction. So that's kind of an overview of that. Now I'd like to be able to show you the actual equipment that I'm using. And it's in here someplace. And I can go down here and do it this way. So this is the actual equipment that I'm using. This is a 14-inch telescope, and mounted on top of it is a 100mm refractor. So this telescope right here is a reflecting telescope. It means it's got a mirror in the back, which is 14 inches in diameter. It's got a smaller mirror in the front, which is about 2.5 to 3 inches in diameter. So the light comes in here, bounces off the primary, goes back up, bounces off the secondary, and then comes back out the back end to a camera that's mounted right here. Now I can also take that mirror off the front and put in another lens up here and attach a camera to that. And that's called a Hyperstar Lens. When I put a camera in the front, I have a much wider field of view, almost 3 degrees, maybe 4 degrees field of view. But from the back, I have a ½ degree field of view. So I can literally reconfigure this telescope and see either something like the Hubble Nebula or almost all of the Andromeda Galaxy. And the mount that I'm using right here is called a Loss-Mandy mount, Titan 50, just for the detail on that. It's on a pier that was actually made by one of my friends, and he's here tonight, Stephen Eubanks. Stephen, that's his sideline job, is making these piers, astrophysics. So that's just kind of like the interior. And you'll notice that I've got it completely paneled all the way around with a rubber mat on the floor. That helps my feet a lot. So there's a view with the roof rolled off a little bit, not 100%, and the telescope sticking out the end of it. Let's go back and look and see where we're at with this guy.
John?
Yes?
Is that an equatorial mount for the purposes of tracking?
It's an equatorial mount for the purposes of astrophotography.
Okay.
So with for an equatorial mount, we can go back to that really quick and look at it in this position. So in an equatorial mount, this arm right here is called the declination, and this one is called the right ascension. So right ascension simply means if you were facing north, the sun comes up from your right hand. So that's rising to the right, or right ascension, and goes all the way down to the west. So from east to west, facing north, that's right ascension. And the motor drive for this thing just rotates this about this axis. So if I point it to the east, then the motor only has to rotate the telescope until it gets perfectly pointing north, at which point this is going to be horizontal. And then I have to flip everything around so that I can continue tracking to the other side. So flipping a telescope around is interesting.
Is your telescope tipped this much to see Saturn tonight?
It's actually tipped in the opposite direction from what you see there, but yes.
But is it tipped it that much?
It's tipped about that much. So if you were to imagine, here's the front of it here. If we were to bring that around to the front toward us, then we would be looking actually to the southwest, because that's the
Yes.
direction that Jupiter is going
You know,
now.
some of us are afraid that Granite Mountain might be in the way of seeing this.
Yeah, from
with our
where you're
naked
at in
eye.
Prescott, it would be. So where I'm at in Paulden, it's not in the way.
Yeah,
Granite
okay.
Mountain is quite far south for me.
Thank you.
So that's a quick overview of my equipment. There you see a smaller camera that I have on the back end. The one that I've got on there now is bigger than this. This is only a it's a 9 megapixel camera. So I've got a 24 megapixel camera on there now. And this camera is a Canon camera, and it's a 24, 23 megapixel. And it's just mounted permanently on that 100 millimeter. I never take it off. So I can swap cameras around here and get different fields of view. So let's go back and look and see what's going on with our Jupiter. So now we have Jupiter, it's getting brighter and brighter. And there's Saturn. And we still have pretty much of a blowout here. And if I were to increase this even more, let me take another snapshot and see what it's doing. There we go. So the sky is actually getting a little darker. So even with the 0.04 seconds, we can now see a little bit more of Saturn in there. And the sky background is starting to show darker. And we have a change in the histogram as well. So let me try going up to 0.05. It's just increasing this a little bit at a time. And eventually we're going to be able to adjust the exposure so that we can actually zoom in and see the rings of Saturn. But we will never be able to see the bands on Jupiter. It's just not that good. Turn this off. So no matter how much I zoom in on this, the other part of this is focus. If the focus isn't exactly right, then you're going to have difficulties looking at anything no matter what. And over here is my focus control. So I can move it in and out by certain steps, or I can even say, go to a specific location. So right now I've got it set for, none of these numbers are absolutely meaningless. They're relative numbers to the position of the motor for the focuser. And what the focus motor is doing is it's right here is an electric motor that's literally rotating. And when it rotates, it drives this mirror in and out. And by moving the mirror in and out, we're getting, that's how we focus this particular telescope. Another way to focus a telescope is like with this one up here. You actually have a focus control here, and it moves this entire shaft in and out. And that's how you focus a refractor. I could have a similar focus control out here so that I could lock the primary mirror in place and just do the focus out here. And that would give me a lot better control over the focus. One of the reasons for that is if the mirror is not locked in place and I move the mirror from one side of the pier to the other, the mirror might flop a little bit. It's going to move just a tiny bit, and that's going to make everything out of focus. So I have to refocus when I move the camera or the telescope from one side of the pier to the other, or even just move it up and down. So the focus on this kind of a telescope will vary if you have to focus it by adjusting the mirror. So it's much better if you're able to focus out here where the camera or eyepiece is attached to.
John, where is the motor?
You can't see it, but there's a tiny little piece that's sticking right here. I don't think I have another view that actually shows it any better. No, it's hiding. It's hiding back in here. It's a little tiny thing, hardly bigger than my thumb. And it's controlled by this device down here. Here's the hand control for the focus motor. Here's the hand control for the telescope itself, for the mount, to move the mount around. And I'm actually inside my house. I'm not out there in the observatory. I like to be inside my house when I'm doing astrophotography or any kind of astronomy work, because it's nice and warm in here. Out there, it's super cold. I can stand, like 2 nights ago, I was out there when it was freezing, And maybe 5 minutes after I was out there, my fingers were so numb I couldn't move.
How do you get the picture from the telescope into your house?
Out there in the observatory, I have a router. It's called a mesh router. And it talks to my router on the inside with Wi-Fi. So I don't have a direct connect going between my house and my observatory. I'm using Wi-Fi to connect to everything. So I've got my internal master router here. I've got another satellite at the other end of the house, which is 50 feet away. And then in the garage, which is another 100 feet away from that one, is another satellite. And they are all three alike in one regard, that they have Ethernet ports on them as well as Wi-Fi. So thank God for the Ethernet port, because literally from inside my house, I can bring up an application that can talk to the mount using the Ethernet port or the Wi-Fi, it doesn't matter. So right now I've got my mount connected up to a computer in the observatory. And then I'm literally, what you're seeing here, this window is a window to that computer. So I'm sharing the one computer to this computer in the house using Wi-Fi. It's an amazing technology, really love it. Now this application that I'm showing you here is called Sky Safari. Sky Safari is a planetarium program, and it lets me see objects in the sky and gives me information about them. And I can actually, there's one here called Telescope. I'm going to connect to the telescope. So now this application is literally talking directly to the telescope, and we can see by this configuration, that's where it's pointing to. So I'm going to zoom in again so we can see what the telescope is actually looking at. So it thinks, here's Saturn. Now in the other view that we had, in this view, Saturn is pretty much in the center of that field of view. Not quite centered, but it's close. So this view right here is a little bit off. So I'm going to click on the Align button, and that's going to, well, let's see, I can't do that until I tell it to look at Saturn or Jupiter. So I'm going to tell it that I want to look at Jupiter. So now Jupiter is centered, but the telescope is off. So I'm going to hit the Align button, and that's going to move my field of view of the camera over to where the actual object is. So now this blue square rectangle that you see here is the field of view of the camera. This inner red circle is a ½ degree circle, and then this one out here is a 2 degree circle. And if I zoom out even more, the next red ring that you see here is a 5 degree circle. So that's 5 degrees from the center, or edge to edge. So if I were to put the moon in here, the moon would literally fill up this inner circle, 100%. So that's called a TELRAD view, T-E-L-R-A-D, TELRAD view. This green line that you see right here, that's set at 20 degrees above the horizon. That tells me if anything goes below 20 degrees, it's actually in that part of the sky where the atmosphere is so muddled up and it's really hot. There's a lot of moisture in the air. So if I take any pictures of anything below that line, it's not going to come out as well as if I take a picture above that line. Now we're going to see Saturn and Jupiter actually come down to about here, close to 17, 15 degrees. And that's going to be about the point, my lowest that I can see with my telescope will be right around in here. Anything above this, my telescope won't be able to see. And that's because the telescope and the wall come together, and the telescope is actually inside the shed. So I start looking at the wall instead of looking at everything else.
John,
So
is the yellow line the ecliptic or the zodiac, or?
the yellow line is the ecliptic, and this white line is the celestial equator. So
Okay.
you can see the sun. The sun is right now on the horizon with Mercury. So that's why things are getting darker. And eventually the sun, when it gets down below, then the dark area is going to get much better so that we can get a better view of it. Now this line right here going straight up and down, that's the meridian. So the meridian divides the sky from the east and the west. And it's the imaginary line if you were to stand facing north and look straight north and then go straight up to the midheaven, that would be the zenith, and then turn around and face south and go right straight down. That's this imaginary line. So you can see Mars is over here on the ecliptic, and there's Uranus out there on the ecliptic. Here's Neptune, and there's the moon. Now the moon today actually is on its first quarter as well. So we're seeing a first quarter moon, so it's going to be pretty bright, but it's still not so bright that I can't pick out objects in the sky and show you some of those objects that are out there. And we can do that as we get closer to 6:30. I'll be moving around. I'll look at a globular cluster. And after we see the globular cluster and explain what that's about, we'll move over and take a look at a galaxy. And the galaxy that we'll be looking at is called M81 and M82. They're pretty close together. And they're out there, you know, where the Big Dipper is. They're pretty close to the Big Dipper. All right, let's go back and take another peek and see what's going on with our Saturn and Jupiter. So there's Jupiter, there's Saturn, and I should be able to increase this to, let's say, 6. When it gets to 0.1, that's going to be our best view, and that's when we're going to be able to see the rings of Saturn. So I'm going to zoom in and adjust this. So very faintly now, I can start to see a little limb on either side of this object. Very faintly. So if I were to zoom in even more on that one, I figure out which way my controls are. Okay, that one. So you're now seeing a very definite oblong shape in here. Now, it could be that my focus is out a little bit. So what I'm going to try to do is adjust this focus and see if I can't bring it in a little bit. I'll go to that setting. Let's move that focus to that point, and we'll see if that's going to change at all. So I'm waiting for both these lights to go red. All right, and I'll take a snapshot and we'll see what's going to happen here. It actually got worse, didn't it?
Well, you can see a little space between the ring and the planet.
I don't even see, all I see is a very light blur. So I think it went in the wrong direction or too far. So let's make that 0, 0.
You got to go out there and wipe off the lens with a cloth.
Yeah, well, I did that last night. I cleaned it off pretty good. Take another snapshot and see if that's going to make any difference. Yeah, you see it now. We're getting a little better definition in that. So maybe what I could do is bring this down to 3990. I think that's where it was at. Let's go to 85. And then take a snapshot. And see if that gets worse or better. That got actually better. You can actually see space around it.
Yep.
So now we're actually seeing the ring of Saturn. Now we're never going to be able to get it so detailed that we'll be able to see what's called the Cassini Division. The Cassini Division is a black line that occurs right through the center of that ring, goes all the way around it. And that's the separation between one half of the ring and the other half of the ring. It's a major separation. There are other dark lines, rings in the rings of Jupiter, dark lines, but the Cassini Division is the one that's most prominent. And it was discovered obviously by Cassini when he got a good enough telescope to be able to see it. So we're not going to be able to see the Cassini Division in this. However, if I were to take the camera off and put an eyepiece in there the eyepiece is going to give me a sharper resolution than the camera will. And with the eyepiece in there, I can actually see the Cassini division. So that's going to be the main difference between using a camera to look at something and using an eyepiece to look at something. The eyepiece in a telescope is always going to give you a sharper view. However, what you don't get to see with an eyepiece is the true color of something. As an example, when we look at something like the Orion Nebula, it's got quite a lot of color into it. Another one would be the Ring Nebula. The Ring Nebula has actually got 3 distinct colors to it: red, yellow, and blue. And when you look at the Ring Nebula in an eyepiece, it's kind of muddy red, and you don't really see the yellow, and you can't see the blue at all. So with a camera, we can actually get those images. And I can actually show you some of those images here. So let me take a look and do a search for Ring. And there it is. So you'll notice the color that we have in here. I'm going to zoom in on that a little bit. So we have definite red, definite yellow, and on the inside is kind of a blue-green. So that was a picture that I took with a not too good of a camera, believe it or not. So, and that's called M27 is another name for it. Oh, that M57, sorry. So I have some other images of the Ring Nebula. That's a little fuzzy. You can see more green in this one, blue-green around this edge. So that other one, it showed this more yellow, and now this one is more green. So again, the different kinds of cameras that you use and how you process the image is going to determine the colors that you get. Going back here, take another snapshot. So as it gets darker and darker out there, this histogram is going to move further and further to the left until eventually it's just going to be a straight line right along the edge.
John, the colors that you showed on the nebula, are they more a function of the material or the temperature?
Both, the temperature and the material. So here's the way the colors work. Anything that is actually really, really super, super hot is going to be blue. Anything that's cold is going to be red. So when we look at a star color as an example, and we see a red star, it's a cold star compared to a blue star, which would be hot or hotter. Now, the colors are also a representation of the actual element. Hydrogen is when you light up hydrogen, you pass light through it or heat it up and it glows internally from its own temperature, it's going to have a red appearance. Oxygen is going to have kind of a bluish green appearance when it emits light. And every element has a specific color pattern to it. So when we take and look at the color patterns that we get out of different places, whether it's a nebula or a star, we can actually identify everything by percentage that makes up that object. So it's either going to be 90% of one and 20% of other things and so forth. And what we found out is that hydrogen is the most abundant element in the universe. And then the next element after that is helium, is the next most abundant element, and so forth. And when we compared the abundance of elements in the universe as a whole and the abundance of elements in our body, it's almost a perfect match. So, I mean, you literally are star children. You are the children of the stars. Yeah, it's almost a perfect, especially for the first 11 elements that are found in the universe and in the body. They're almost 1 for 1 in percentage-wise.
Are those the correct proportion to the atomic number?
I'm not a chemist, so I can't talk about atomic numbers, but you may be right.
I mean, could you just go right down the periodic chart?
Not quite.
Okay.
Not quite, because the heavier elements, yeah, again, I'm not a chemist. I didn't study chemistry. I flunked out of chemistry, in fact. I had to get out of there after the first 2 weeks. So, so that's, but even at that, you know, astronomers know the periodic elements fairly well. And I'm not even an astronomer, so I didn't even make it through a full session of, I did Astronomy 101 in 1951, and that was the breadth of my astronomy experience. But since then, I keep abreast of astronomy as a hobbyist. So there's a lot of things that I have special interest in, like how does a star get formed? And how does a star die? What happens when a star dies? There's several different ways that a star can die. Our star, when it dies, literally is going to become a white star, a white dwarf. And all of the elements that it was holding on to is going to get shed off and become a nebula, just like that ring nebula that you saw. So our star is going to, you know, in 5 billion years from now, to somebody looking at it from another galaxy or another part of our galaxy, they're going to see possibly a bubble nebula or a ring nebula, one of those two shapes.
Yeah, this is Jeff. Does the colors that we see have anything to do with the term redshift, or can you describe what redshift is?
I can describe redshift. So if we take a look at hydrogen as an example, and you look at the spectrum, the light spectrum of hydrogen, you'll see dark bands in that spectrum at specific places. And then when you take a look at helium, those bands will be in a different location. And if we look at, say we've got a ball of hydrogen gas that's a foot away from us, and we take a look at the spectrum and we see, okay, here's what the spectral pattern looks like at a foot away. And then we take it and we move it 2 feet away. What's going to happen is those lines are going to shift a little bit to the right. The farther away you move the object from you, the farther to the right those bars shift. That's called redshift. So when we look at something that's really far away, the hydrogen, the bars that specifically identify hydrogen are going to be moved so far to the right that, you know, we can actually say, well, we know if we move it from 1 feet to 2 feet, how much it shifts. If we move it from 2 feet to 4 feet, we know how much it shifts. We keep extrapolating on that, and we say if we move it 5,000 miles away, we're going to see this much of a shift. Well, if we see this big shift, then we can calculate how far away that object is. So
that's also proportional to the speed with which they're receding from us?
Yes, that's the Doppler shift, and that's another aspect of it. So as something moves away from us, it actually creates that Doppler shift in the light and makes it look more red as it's moving away from us. And as it's moving closer to us, it makes the light look more white. So let's say if we have a perfectly white light and we have it at a certain distance and we see that it's white, and then we move it, then it's going to appear red as it moves away from us. If we move it closer to it, it's going to appear blue as it moves closer to us. And that dog is laughing at me, I know it.
Sorry about that.
Okay, so there's the rings of Saturn showing up pretty good.
Yeah, I had asked in chat, but not sure if you're watching. I was just wondering, as it gets darker, and you're able to adjust the aperture and speed, will we be able to see any moons of Saturn?
Oh, yes. Well, there's going to be one point right close to 6:15 when I can actually adjust the, bring this exposure time up to like 1 minute or 2 minutes. We'll be able to see the moons of Saturn, and Saturn will be blown out. It'll be just a white blob. And Jupiter will also be blown out, another white blob. Let's come down here and see if we can see anything at all of the moons of Jupiter right now. So as I move in on that, now, as you can see, there is a little bit of a band that we can see across here. So that's exciting. I can see another band right here a little bit. And then there's a little darker band up here at the top and at the bottom. So we're able to see some of the color variations in Jupiter at this point in time. So let me zoom out a little bit, and I'm going to increase the exposure to 0.1. And let's see if we can't pick up some of the moons of Jupiter. Not yet. So even at 0.1, we still have pretty good color in there. So let me bring that up to 0.5 and try to get the moons in there. So when this blurs out completely and becomes a white blob, then you'll know we can see the moons. There's one right there. And there's another one right there. So let's increase that a little bit more. Let's go to 8.8. Nope, don't want to go to 8.8. Here we go.
Okay.
So there's 1, 2, here's a third one. Now, there will be a time when you're only going to see like 3 moons, and that's because one of them is hiding behind Jupiter. And there may be times when you only see 2 moons because 2 of them are hiding behind Jupiter. And then there's times when you see no moon. They're all hiding behind Jupiter.
What's that thing on the top right? That's Starship
Saturn.
Enterprise? Oh,
That's Saturn.
Okay.
So there's your telltale ears on Saturn. So this is pretty much what was seen by Galileo when he took a look at Saturn. All he could see was the ears. And that's the way he described it. I think it was Galileo. So let's go up a little bit more. See, we're actually getting to where 1 second, and see if we can't pull in more moon. And I think I can get the moons if I do this. No, that made it worse. There's one right there. 1, 2, 3. And the 4th one is going to be lingering right close by. Now, some people might think that one of these objects way out here might be a moon, but I really don't think it would be. This would be the farthest out. Now, Titan, the moon of Saturn, is going to be really, really close in, but when we get enough exposure and it's dark enough and I'll be able to zoom in on that, then we'll be able to see Titan, which is the moon of Saturn. It came in quite clear the other night. It had about a 4 second exposure to get it. Don't know how 4 seconds is going to do. I think it's too bright out there for 4 seconds. Yep. 4 seconds is total whiteout. Too much. Go to 2. 2 might be too much. So as you can see, we play around with the exposure quite a lot. So 2 seconds is the most I can get out of this. If I go up any higher than 2 seconds, it's going to literally wash out the sky. So zooming in on Saturn, I don't see any little blobs around it yet. And it would be pretty definite if there was anything. So as it gets a little darker, like I say, closer to 5:15 or another half an hour from now, we should be able to see that. Looks like there might be something hanging around right around in this area. I saw 2 moons down here and then Titan over here in this area. And that was the other night. So don't see anything there now. So coming down here, back to this one, let's see how many moons we can pick out. Well, there's definitely one right there. And if you'll notice the shape of it, it looks like it's got a little point sticking off of it. That's caused by not being perfectly focused. So there we go. We're just seeing 3 of the moons right now. So one of them's got to be hiding behind Jupiter. 2 nights ago, I was monitoring it, and one of the moons is just slowly disappearing behind Jupiter. So yeah, it may be coming back around to this side eventually. So you're beginning to get a feel now for, what we do as amateur astronomers to try to get pictures. And this is only the beginning of it. So as I continually adjusting this exposure to get different views, now we can, I can zoom in on Saturn at this point. Now, another thing that's going to be happening as the sun sets, the air gets colder, that changes the temperature of the telescope. As the temperature of the telescope changes, not just the tube itself, but the mirrors are the most important thing. The mirrors will be changing their temperature, and you have to readjust the focus as the temperature changes to compensate for the change in shape of the mirror itself. So let me see if I can bring this up to 9.5 and see if that's going to make any difference in that focus. Kind of did. I think it improved it a little bit. So I'm going to go up to 0.5 on this and see if I can't get a little bit better representation, a little more exposure, giving more detail. So there we see a little bit of detail. It looks very fuzzy. Now, most of the fuzziness is caused by the atmosphere. So I can't really blame the telescope being out of focus too much, but I'm going to make another adjustment in here to see if that, which way it's going to go in or out. And even on a really, really good dark night, I cannot get a sharp image of Jupiter or Saturn. Now, what we do to capture an image of the planets and make them nice and sharp is we take a video. So we'll run a video for, oh, there we go, much better, 990. So that's good. So that's probably the best I'm going to be able to get. We take a video, and at 30 frames, let's say the video is 30 frames per second. So we're going to run the video for 5 minutes. Now, 30 frames a second, that's 180 frames a minute times 5. That's, we're getting up there. So sometimes what we'll do is we'll get 1,000 frames in a video and then run it through a software that takes those separate frames and lays them one on top of the other, stacking those frames. So we're stacking them. And then what that does is it averages out all this fuzziness and gives us a sharp detail. And also in the stacking process, what it's trying to do, as the planet is shimmering out there in the sky, it moves back and forth a little bit, or shimmers, or it expands and collapses. There's all kinds of shimmering that goes on. And the software takes all this into account from frame to frame and says, well, here's my reference frame. I'm going to use this for a reference. Everything else has to fit that reference. So I'm going to readjust the size of this one to fit over that one. So it does that for all 1,000 frames or so. And that's where you get the really sharp, detailed images.
Gesundheit, John.
Yep, thank you. So picture this at 0.1 degree. So let's go back to a full view. So again, this is 1/2 a degree, 0.5 degrees. So this is just 1/5 of that total width, or 0.1 degree. So again, the moon will fill this entire area right here if I were to take a snapshot of the moon. Well, why not? Why not take a snapshot of the moon? So let's find out where the moon is at. So I'm going to use this one right here, and we can see the moon is right there. So if I click on the moon, now you can see that it's got little lines around it saying the moon has been selected. And over here it says the target is the moon. So yeah, let's go to the moon. Now we're going to see the area around. We're tracking the telescope at this point in time. So the telescope is having to go from one side of the pier to the other side of the pier. So we're actually following the telescope as it's moving through space, so to speak. So here's the north, and there's the North Celestial Pole. And when I park my telescope at night, it's looking right here. And after I unpark my telescope, I have to set it up so that it's looking there. So now we're moving over. We're going to get a shot of the moon. And I have another piece of equipment that I can show you. Come on. Where did you go, guy? And this guy right here, I want to bring this up. So this is looking at another camera. This is my guide camera. So we're going to connect everything up, make sure that this particular software called PHD2, it's connected both to my camera and it's connected to the mount. And when we take a look and see what's in there, now notice the exposure here, 0.01 second, and right there is the moon as the guide camera is looking at it. So you can see pretty good definition in the moon there. So let's come back over here and see what this is going to do. Now for this one, I'm going to have to bring that exposure way down. And now I'm going to take a snapshot and we'll see what the moon looks like here. There's the moon, and the exposure needs to go down even more. So let's try that one so that we can see some detail in here. Now the moon didn't exactly center, and there's several reasons for why it didn't exactly center. But since we're looking at a very narrow field of view here, the fact that it is in the field of view is good enough for me, because I can always use these controls over here to adjust it to bring it into the field of view. Now that says that it's an error message. That's not going to work. Let's try that. See if it likes it. Didn't like that either.
John, you may have a double decimal point in there.
You're right. That's what's going on. Thank you. Because I know 06 should have worked. All right. So 60 microseconds is actually the fastest that I can do. And you'll notice it turned completely black. So 60 microseconds is just too fast. So I'm going to have to go down from 60 microseconds to 0.0001. We'll do that and see what that's going to do. And this is 0.1 millisecond, so possibly 0.1 or 1 millisecond. Let's take a 0 out, try that. A lot of fudge factor going on here. So that still appears to be not enough exposure. There we go. We're getting in there. So I'm going to try 5. Okay, so now we're getting a pretty good representation here. And I'm going to click this and no, so that's too much actually. Now the difference between this being on and off, when it's off, then we're seeing the raw image without any adjustments. And when we say no adjustments, that means we're looking at the full field of view here. And with the adjustments in there, then it attempts to automatically just look down in this area where the actual object is. So even 0.005 is too much for that. So let's add another 0 to that and see what it's going to do. There we go. So it's not the best image. And again, in order to get good images with this, we would again try to do a video. So I'm going to put this into a loop mode, and I'm going to bring that image down by using the control here. And I have 3 different speeds that I can control it at. There's a guide speed, a centering speed, and a slew speed. And then we can move it a little bit to the right. So let's see. I always forget which one of these buttons to push to go to which side. So let's see what happens if I push it here. Yep, that's the right one. Now, the other thing that you need to pay attention to here is the object is actually flipped left to right. If you were to go outside and look, it's going to be lit up on this side, not that side. So we're looking at the image flipped. And that's caused by the lenses in the telescope. So we can start seeing the craters in here. So as I zoom in, and we actually have pretty good sharpness and detail. So the focus is pretty good right now for this. I probably wouldn't mess around with the focus at all in order to get any more detail out of this. But looking at the edges of the moon right here, yes, there is a possibility that we could get a little bit better out of it. And looking, it's pretty washed out in here, so definitely that could be improved. But you see the different oceans or mares, not lakes actually in one sense of the word, and the craters. These are craters. These are all craters, by the way, every one of these. But they were called mares or lakes or oceans because the first astronomers thought they were actually water mass on the moon. Just like on Mars, when they looked at Mars and they saw all these sharp lines going crisscross across it, they thought, oh, there's civilization out there, and those are the roads. Well, I later found out that they're not roads at all. They're just striations in the surface of Mars caused by different effects. Like they've got a Grand Canyon, which is as big as the whole United States on Mars. Fascinating. So that was like a trip to the moon, and that was pretty quick and easy. So we can take another trip right now and go back to where we were. So let's take a look at Jupiter again. And all I got to do is tell it to go there. And Jupiter now is the target, and we'll say go. And we're going to be able to see what happens as this thing moves. Notice it's going in the opposite direction because this is the meridian now. We can't cross the meridian to get to it. We have to go around the horn, through the North Pole, and come back up the other side in order to get to Jupiter. And Jupiter right now is, let's see if I center this. That tells me that Jupiter is at 16.7 degrees. So we're still well within the area that I can look at. I can get down here. I might be able to look at Pluto, but it's so teeny tiny right now, and it's in pretty much of the bright area of the sky that I seriously doubt we would be able to see much of Pluto. In order to see Pluto with this telescope, it would have to be pretty much straight up in the sky and super dark with no moon. Here we come, coming around the horn, picking up on Saturn. So let's go take a look and see where we're at here. Now again, I have to adjust the exposure because we had to readjust it for that one. Let's turn the looping off. Well, we actually saw it a little, I think. So let's go to 0.1 and see how that's going to look. Look at that. We see very distinctly 3 moons. This is not a moon. That's got to be a star. Now here's how we can find out for sure whether that's a moon or not. By using this application, zooming in on it so that we can see where the moons are situated on Jupiter. We see 1, 2, 3. The fourth moon is actually hiding. Ganymede is out there. It's either crossing over the equator, which is what it looks like it's doing. So Ganymede is actually crossing the equator. So we got 1, 2, 3 in that arrangement. Looking back over here, there's 1, 2, 3. This is not a moon of Jupiter. We would like to think it would be because it looks like it could be, right? Now, what we're noticing here, way out here from Jupiter, Iapetus is actually a moon of Saturn sticking out here. So we have a bunch of these moons close in, and then Iapetus is way out there. So we don't have anything else that's way far out in this line that would represent a moon. So the only thing that I'm showing are moons and planets. I'm not showing any stars. So it would have to be a star that we're seeing way out here. Don't think it could be Iapetus. So yeah, it's not even in line. So we saw one that was out here, something that was really bright in that area. So that's not it. And then let's see if we can come in now and look at some of the moons of Saturn. So we should be able to pick off some moons of Saturn. Titan, right there. Now, it definitely looks a little blurry to me. And when it looks blurry, there's almost a donut shape to it. That tells me we're definitely not focused. So I would have to change the focus here to try to get it in. So as it gets darker and darker, this object is, it'll blow up and look like a donut with a hole in it. That's how much out of focus it can get. When it's a sharp point, then we know that we got it in focus. See if that little bit that I moved is going to make any difference at all. Oh, it made it worse. So you mean I got to go in the opposite direction? Instead of that, I need to go to 8.5. We got 69 people observing right now. That's amazing. Okay, much sharper. I could probably tinker with this until I can get it nice and sharp. Probably isn't worth it, but just for the heck of it, I'm going to try 8.2. Now this software that I'm showing you right now, it has an autofocus feature to it. And when I use the autofocus feature, what it'll do is it will defocus until we get a big donut, and then it'll work its way down, smaller and smaller, tighter focus, until it goes back in the opposite direction and becomes a donut in the opposite direction. And then it does a calculation on this curve. It's either a big donut over here, a little dot here, and a big donut over there. So somewhere in this area, it's a nice sharp dot. So that's where it will move it to. And that's what the autofocus software does for me. And that's what this one is for right here. So that's my autofocus button. In order to use the autofocus button, I have to have at least 30 good stars for it to look at. If it doesn't have at least 30 good stars, so it's not going to work on planets like this. And it actually doesn't work too well on galaxies, because galaxies is a big smudge ball in the sky. So there's another moon of Saturn. And there's another one.
John, I have a question for you.
Yes.
Now, these two look side by side, but how far away are they in the depth proportion and the depth distance?
In the depth, they're 455 million light years apart.
Which one is further?
Saturn.
Saturn, okay.
So Saturn is farther away by 455 million years away. Yeah, million years. Now, in terms of time, some people ask, how long does it take for the light from Jupiter to reach the Earth? Well, that actually turns out to be 49.3 minutes.
Wow.
And for Saturn, it's 90.06 minutes.
So what we're looking at now, it happened 49 minutes ago.
Yes, at least. So we're seeing Jupiter the way it was 49 minutes ago. We're seeing Saturn the way it was 90 minutes ago. So that means these moves have actually moved around since then. They're not there anymore. And if you keep watching hour by hour, you will see these moons shift in their position all the way around. Here's another moon sticking out there. I hope it's a moon. Let's take a look and see what this guy says it is. So we see Titan off to this area. Then we see Rhea, which is over here. And see if I can zoom in a little bit on this. Hyperion and then Iapetus. Now we probably won't see Iapetus because it's a little tiny thing, but we might want to believe this has got to be a star. It's not in the same grouping. So this one may be Iapetus as a possibility. So that's why I'm using these planetarium programs. This one is called Sky Safari Pro and version 6. There's others like it that are free. This one costs about $40. I think they had it on sale for $25 not too long ago. Stellarium is another planetarium program that you can use. And there are still other planetarium programs that are free. Here's one called Carte du Ciel. And this is French for sky chart. There's the sky chart of the sky. So sky chart is a free program. And that's what I'm actually using at this point in time as a possibility. Notice the 3 rings here, the ½ degree ring, the 2-degree ring, and the 5-degree ring. This is called Telview. Did I say that right? Teleview, no. I forgot the word already. How did they do that? Anyway, it's just a way to observe, you know, how far apart are things and how far do we have to go. So if I was wanting to find this star as an example, what's the best way to find it? Go to some nearby bright star that I know where it's at, and then see if it's inside the ring or outside the ring. That'll tell me how much farther I got to go to get there. So with this one, I can actually look and find different objects in the sky, like M15. M15 happens to be a globular cluster. And that's going to be one of the objects that we'll look at in a little while. And this circle that you see here is the expanse of the M15. We'll most likely just see the stars in the inner part of that globular cluster. And then when we look at M82 or M81 as an example, notice this galaxy has an oblong shape. We're going to be looking at that galaxy. So by using this star chart, I can pinpoint it here. I can say, okay, this is what I want to show. Let's go over here to this program called framing and pick it off. And it's going to tell me it's M81. It's at this position. It's going to show me a picture of it in the middle here in a minute. And when it does, I can say, go to that point. And then I come back over here and I look at the object and it'll be in there or close. It'll be close. May not be perfectly in the center, but it'll be close. And then I can make the adjustments using this software. So right now I'm using 1, 2, 3, 4, actually 5 pieces of software because there's one more. This one right here is the software that I use to control the focus motor manually. So I can actually connect to that focus motor that's on the telescope and move it in and out with this just by clicking on the connect. Let's see what happens when I click here. Failed to connect. Yep. And that's because this software is using it right now. So I can't use this in conjunction with that. But the interesting thing is this software is using the interface to talk to that controller. We saw that hand control sitting on the desk earlier. So this software is actually looking at it. And that's where I go into this to say, I can connect to a camera. I can turn the temperature, so I can adjust the temperature to what I want it to be. I can adjust the default gain and offset settings. And here, if I had a focus wheel or a filter wheel, I could connect a filter wheel to it. Here's the focuser, I'm connected to that. Down here is a rotator. If I had a rotator on that camera, I could rotate the camera precisely in degrees from 30 to 180 or whatever I needed to. And here's the telescope itself. I'm connected to the telescope, and here I can control it manually, or I can put in the target angles of the right ascension and declination for an object, slew to that object. And then we come down to the guide scope. So I've got the guide scope connected, and it's looping, and this is what we're looking at right here. So as I click on this, it says, find me a star, so I can guide on that star. So once I see this green crosshair here, that tells me the telescope is now being controlled by this software to perfectly track that object that we see in our field of view, which is Jupiter. So right now it is tracking Jupiter precisely. So it's not going to shift left or right because this is controlling it. This is keeping it in position the way we need it to be in position. And that's also controlled by the time down here. So right now it's a pretty tight time. I mean, that's really too tight. So if I go to 0.1, that's a little bit larger exposure. Now we can see Saturn in there, and we can see that Jupiter is getting a little bit larger. As I increase the exposure here, pretty soon Jupiter is going to blow up and be a little bit larger, and it's going to be actually too big to fit inside that little square. So that little square that we see right here is the area within which this object must stay inside of. So if that object moves one way or the other in any direction, the software is picking that movement up and deciding which way and by how much it has to move the telescope to keep that perfectly in line where it was. So now we can see the moons a little bit better in here. This has got to be a star. That's got to be a star. They're just in the wrong position. This one here was probably really close to that moon the other night when people thought they saw 5 moons. That was another star that would happen to be right next to the moon. So we're still seeing Ganymede is still hiding. It's either in front or behind Jupiter right now, so we can't see Ganymede. So what I was looking at here was, let's go back and change this to M15. And I'm going to click on that guy and say, yep, this is what I want to look at. And then we come back over here to our framing adjustment. Click on this to say, go get the coordinates from that sky chart. And it's going to show me, say, there's the galaxy that we'll be looking at later today. And then when this finished its circle, it's actually looking inside of a database here, NASA Sky Survey. It's looking inside that database to find what that part of the sky will look like for us to look at. Notice there are 3 galaxies here. This is M82, this is M81, and I don't remember the name of that one. I should. This is probably a galaxy 2 right here. In fact, there's actually no place in the sky that you can't look and not see a galaxy. So there's this globular cluster, pretty tight group of stars. And some people might ask, how does a globular cluster get made? What makes it happen? Wow, how does it get to be a globular cluster? Well, a single star is made by hydrogen gas collecting in a given area. And as more hydrogen gas collects, it creates a gravity well to pull in more hydrogen gas, which creates a heavier gravity well to pull in more hydrogen gas. And as you pull in more hydrogen gas, this gas on the outside is putting pressure on the gas on the inside. When that ball gets tight enough for the pressure on the inside to actually start nuclear fusion, that's when 4 elements of hydrogen actually merge and become one new element. And when they do that, they give off photons of light. And that light now has to escape out of this ball of hydrogen gas. And it could take 1,000,000 years for that ball of that little tiny speck of light to bounce around inside that hydrogen ball until it gets outside. And then from the sun to the earth, it only takes 8 minutes. But it could take 1,000,000 years from the inside of the sun to the surface of the sun for that little tiny ball of light to get out, that photon. So there's M15. So let's see what happens. In order to actually do that, we're locked in right now on Jupiter. We're doing a slew. So I have to unlock it so that I can then do a slew. So we're not locked into Jupiter anymore. So that means we can move the telescope. So now I'm going to slew, and that's going to move the telescope. So let's watch the telescope move. And I think we're in too tight right now. Where did it go? Where did it go? Let's lock on it. There it is. So it actually made it to M15. So there's M15. There's the field of view of the camera. And here's the group of stars. So now I explained how a single star gets ignited. So this group of stars got ignited the same way by this huge, huge, huge ball of hydrogen gas collapsing down and getting so much pressure on the inside that in several places inside this ball of gas, several stars ignited all at once, or within a few million years of each other or so. But all of these stars literally are in the same family. They were all the same age, relatively speaking. So now let's look over here and see what we have when we take a picture of it. So we're going to take a picture, and it's not going to look like much because the exposure is way too small. So we see nothing but a dark sky and a few little spots in there. So I'm going to turn this up to like 10 seconds. And let's see what happens at 10 seconds. And down here we can see the exposure time counting from 5 to 10, 6, 7. And now it's going to de-Bayer the image, and now it's stretching the image. And where is our ball of light? It's nowhere in there. Let's take a look and see what this guy says. So I turned it on. I don't even see it in here. This has a much larger field of view, much, much larger field of view. So if I don't see it inside here, that means we're nowhere close. I don't see anything that would look like a bunch of stars all close together. So this thing lied. So what am I going to do about that? What I have done is I've actually put in some specifications for finding these things, and I'm going to do it that way. So I'm going to come back over to this and come into here and get a look at my telescope, and I'm going to put in the location where it is supposed to be, and that's 21, 29, 59. Moving down to there, the next one is 12, 10, and 12. And now slew. So we can watch and see what's going to happen over here. And it probably didn't shift much at all. It shouldn't have, because now those, what I put in there was pretty accurate. So let's see what this is going to do now for an image. And I still don't even see it in here. I don't see it. I'm hoping I don't have to go up any higher than that, but let's try 20 seconds and see what it's going to do at 20 seconds. Hey guys, this worked perfectly last night. What can I say? Science. Sometimes you can rely on it. You notice we did get the moon, and we were able to go between the moon and Jupiter with no trouble whatsoever. Take a snapshot here. And I'm still not seeing it.
John, where are we in the sky relative to the horizon or the vertical straight?
As far as looking at this object that we're trying to look at here?
Yeah.
Okay, so notice here's the red circles with the tail red image. There's Jupiter. Here's the southwest. Here's Saturn. So it's not, it's kind of like directly above Saturn. If you were to go outside and look, it might be directly above. You wouldn't see it with your naked eye. Here's M2. You wouldn't be able to see that with your naked eye. Here's M72. These are all globular clusters. Here's a couple more globular clusters that are in that area. And here's another one. Now, I know these are globular clusters by that symbol. It's a circle with a crosshair in the middle of it. So any of those symbols that look like that, those are globular clusters, which are tight grouping of stars. M15 is one of my favorites because it's quite large relative to others. And it's a little more sparkly. The brightest and biggest grouping of stars that we can see in the sky, big in terms of relative, the largest grouping of stars relative to everything else in its area would be M13, and that's in the Hercules constellation. So we wouldn't be able to see that tonight because it's already down below the area. So as an example, if I were to do a search for M13 here, notice it's literally out of my view. I wouldn't be able to point to that. Here's the Hercules constellation. Hercules cluster is right inside there. So by the time it gets dark enough to see that, it's going to be literally below the horizon. The other features that you can see here is the Northern Cross. You can see that. And this is Cygnus the Swan. Here's the head of the swan. Here's the tail. There's the wings going across. Here's the summer triangle. You can see that up there, pretty obvious. Those are the stars that form that asterism that we see in the sky. Here's the Great Square of Pegasus. And we have all different kinds of things. Here's Cassiopeia's chair. That's the W that you see in the sky right here. And I like to point out that these two, this angle right here points right at the Andromeda Galaxy. So the Andromeda Galaxy is over here. And if nobody has ever seen the Andromeda Galaxy with their naked eye, then they weren't in a dark enough sky, because the Andromeda Galaxy is 6 times wider than the moon. It's literally 3 degrees wide from tip to tip, and it's at an angle a little bit. So you don't see it face on, you see it at an angle, but it's literally 3 degrees from tip to tip, and it's 6 times wider than the moon. So, and we can only see the very small center of it, which is less than ½ a degree. And that's with our naked eye. But when you look at it through a telescope, it's a totally different story. As an example, let's see if I can find M31 right here. So this is an image that I took of the Andromeda Galaxy. So it literally extends out beyond the limit of my telescope view, my camera view. And these other galaxies in here, this is M110 and this is M32. So these are other sister galaxies or companion galaxies of M31 or the Andromeda Galaxy. And we can see the spiral shapes in here, these dust lanes, very similar to what we have in our galaxy. So in appearance, the Andromeda Galaxy is a lot like our galaxy, except this is more of a true spiral galaxy, whereas our galaxy has the appearance of a bar through the middle of it that the arms stretch out from the tips. So we are called a barred spiral for the Milky Way, and this would be a spiral. Now these clusters of stars around this one galaxy, that makes that a, it was on the tip of my tongue, elliptical. It's an elliptical galaxy because it has no definite spiral shape to it. It's just a fuzzball in space. Same thing with this one. It's an elliptical galaxy. Now, finding Nemo. What happened to my galaxy cluster? Yeah, where's my cluster of stars? They're supposed to be in there. So I'm going to take a chance here, and I'm going to go into this, and I'm going to say it's probably way off screen someplace. And I'm going to come back down here to 2 seconds so that we can get onto a loop here. And see what happens as we drastically move this from side to side and see if maybe that group of stars will show up. It shouldn't have been that far off because we were centered on Jupiter. And being centered on Jupiter, we should have been smack dab on M15. It's not that far away.
John,
Yes.
check your declination in the bottom panel.
Check my declination. What do you mean by that?
You set the declination at 11 and the declination, and here he's 20.
I just lost your voice. You went mute. So it's supposed to be 12, 10, and 12. 21, 29, 59. That's what I had last night. Everybody wants super silent. Okay. So some people are checking out.
We're just waiting with bated breath.
Bated breath. Exactly. Me too. What happened?
12 is not supposed to be a negative 12?
No, it's supposed to be a positive 12.
Okay.
What was the name of that cluster?
M15. Okay, I've moved a whole lot in that one direction. It never showed up, so I'm going to go back in the other direction and see what it does. So those streaks that you're seeing are stars. There it is, right there. See that?
Mm-hmm.
So I'm going to see if I can get that centered. And then we're going to do a plate solve on it to find out exactly where it shows up on this chart. Because right now, it looks like, oops, too far.
I was looking at your declination numbers and those look right. I don't remember what you said the other ones were.
21, 29, 59 for the bright Ascension. And then 12, 10, 12.
Right, 20, 21, 30, 58 right now. Well, that's from my location. I'm sorry. Disregard.
So you're where?
could be close,
You're in northern Canada? No, I'm saying.
Yeah, I'm pretty close.
Okay, so we're pretty centered here. I can probably live with that. So I'm going to do a plate solve on that and find out where it thinks it's at. Now we're going to sync on it, but we're not going to re-slew to it. We're just going to find out what it thinks is going on here. So I turn that off and then turn this on. It's going to do a plate saw by taking an exposure of 6 minutes, look at the image, and then give us a readout here where it thinks it's at. So it says it's 21, 29, 59, and then 12, 10, 11. I wasn't that far off, but yet it went to a totally different area of the sky. So that's just totally surprising to me. So what I'm going to do next is come over to this one and make sure that we're looking at M15.
And John, are we still able to see Saturn and Jupiter?
Yeah, I can go back to that and look at it in a minute. So right now, here's M15. I'm going to do an align on that. So that now, if let's take a quick look at this guy before we jump back over to Jupiter and Saturn. Come on. Every now and then I lose total control. So it looks like, oh, I'm in the wrong one here, image. So there's the image right there. That's the group of stars, but that's only with a 1 second exposure. So if I go to a 10-second exposure on that and take a look, I'm going to turn the loop off. Go to a 10-second exposure, we're going to see a lot more detail on the stars around here. So there it is. That's with 10 seconds. If you want to hang out for 30 seconds to see it at a 30-second image, you see how much more detail is going to pop out. Now notice we're zoomed in, we're not at full view. So there's full view right there. So this is half a degree, top to bottom. So this whole thing is going to be about an expanse of close to 1/4 of a degree all the way around top to bottom. Two more seconds. Now it's showing down here that it's debayering the image. Now it's stretching the image. Now look at how much whiter things are. And that's what happens as you get a darker sky and go to a higher exposure, you get a more accurate representation of color. So as I zoom in on this, we do see still a lot of green tint on here. Now, I don't have any controls on this software to adjust that color, which would be really nice if I had those adjustment colors, that adjustment tool, but they haven't added it, not yet. They might sometime. But we're getting pretty good detail as far as the tightness of the stars. They seem to be pretty well focused. We don't see any blips off to one side or the other. And corner to corner, we have pretty good stars all the way around. So I would call this a good shot for a single exposure. What I would normally do at this time would be to take 30 to 50 exposures and then stack those, and then also merge them with a series of flaps and darks and bias images to get a perfectly clean image. So if anybody is into astrophotography at all, they know what a dark and a flat and a bias is. So let's swing back over now and take a look at our Jupiter and Saturn to see how well we're getting along. There it is. So now we can go to that. And because we lined up on this guy, we should be dead on when we come back to that. Then, of course, we're going to have to come down from there to like 2 seconds, just for the heck of it, just to see what's going on. There they are. Notice they're not quite centered, so we would need to center them. So to do the centering, we have to go in the opposite direction of the, we have to click on this side to move it to that side. Backwards from what I'm normally thinking. And I'm also going to put it into the loop mode and come down to 1/2 second here so that we have a little more tighter control. Okay, so that's pretty close. I'm going to call that one. That's good. Take the loop off. And now we're at 1/2 second and we're literally blowing out Jupiter completely. And when we come in here to Saturn, we can see the moons of Saturn fairly clearly. And, pretty sure these are part of the moons for Saturn as well as these two. So all those are the moons of Saturn. They're scattered out pretty much all over the place. Fortunately, with 455 million miles separation between the two, there's not much chance of the moons of Saturn colliding with the moons of Jupiter. Darn. Not much chance at all. A lot of empty space in here. So that tells you that this is going to be pretty darn big in order to look almost as big as Jupiter at a 455 million miles difference between the two. Now we're starting to also pick up more stars in this. And if you'll notice, there's been a shift in the position of these moons around Jupiter. And if we drop down in our exposure, let's go to 0.1 and take a snapshot and zoom in. See what kind of detail we can get out of this. Oh, you see the streak right there? That streak is a satellite or an airplane, one or the other. Notice it's gone. So even at 0.1 seconds, it's still too much to be able to see definition in here. So 0, let's try 0.1 and see what we can do for that. It's probably going to have to go down to 1 millisecond in order to get the definition. Yep, 1 millisecond. At 1 millisecond, we should be able to see a gap. There's the gap. But then we lose the moons completely. Now looking over here, now we have too much exposure to be able to see the bands in Jupiter, and the moons are just disappearing on us completely at 1 millisecond. So at this level here, you can get the shape that, there's Saturn. Yeah, we can recognize that one. But that's about as good as it gets. On a super dark night, I can play around with the exposure and I can make color adjustments and just a single snapshot of Saturn. It doesn't look much better than that with a camera. But again, if you put an eyepiece in that telescope and look at it, it's going to have a pretty sharp definition, and you'll be able to clearly see the Cassini division inside Saturn with an eyepiece. So I'm kind of disappointed that with my high resolution camera, I cannot see the Cassini division, and that's only because I don't have the right focal length for my camera and telescope combination. I could get there by adding what we call a Barlow. So I could put in a 2x Barlow that makes everything twice as big. So with a 2x Barlow in there, I'm pretty sure I could get a pretty decent view of that. But that would add extra weight to the back end of the telescope. I would have to readjust the balance. So I think what we want to do now is see if we can find M81, the galaxy, and take a look at it, because it's going to be an interesting sight to see. M81. Oh, that's not going to work. M81. So it's over here. Now it's literally on the other side of the North Celestial Pole, and it's getting pretty close to below the field of view, but it's within the area that I can still get a look at. So let's do a go to. Now it says stop, so that means it's actually slowing. We should see it come into view before too long. Don't know how much farther it's got to go to get there. There it is. It's coming down. So in a way, it's kind of exciting to see the telescope in action when we look at it from this perspective. And all this green area down in here, that's the Earth. That's below the horizon. All right, so we're pretty close. So let's increase this to like 4 seconds. I'm gambling that it's going to be in the field of view. There it is. It's almost perfectly centered. So all I got to do is increase this. Now this one here, I definitely have to go to 30 seconds in order to get a decent image out of it. Actually, an even better image would be like 5 minutes, but I'm not going to bore you with a 5-minute view. Instead, what I can do is I can take a look at a previous image that I took the other night, which is actually last night. So here's M81 last night, and just pop this up. It's going to bring up another application. Now, it's in there, but you can't see it until I actually do something to screen stretch here. There it is. So this is a 5-minute exposure of that galaxy. So you're beginning to see, you know, as we get more sophisticated with our tools and techniques, things start looking a little better for us as far as what kind of images can we get. So you can definitely see the 2 spiral arms on this thing, very distinct. And then there's the other part of that galaxy is M82. So when we look at, I didn't want to go there, I want to go here and look at M82. I don't have it in here, why? Okay, it disappeared on me. I know I thought I had it. Is that part of my snapshots? Yeah, part of my snapshots. Here we go, M82. And we'll do a stretch on that guy. So there's M82. So M82, we call that the Cigar Galaxy. And it's also, a lot of fireworks are going in the middle of it. There's a red flare going right through the middle of this thing. So different cameras with different exposures. You can get really interesting features out of the Cigar Galaxy. But the 2 of these galaxies together, let's take a look at them over here. So when we zoom in on this, we'll be able to see how close together those 2 galaxies are. So it's called Bodes Nebula. There's one of them. And I have to change this so that I can see galaxies. So we notice here's the other part of Bodes Galaxy right there. And that's the Cigar Galaxy that we were looking at. And here's M81 that we have in the view right now. So they're pretty close together. I would need a larger field of view in order to get them both. So inside this ring, so if this is 2 degrees from side to side, I would need a bigger field of view in order to see that. All these other little oblongs that you see in here, those are all galaxies. Down here we have the Cardigan Nebula. He called it a nebula because he didn't know it was a galaxy. So things like that happened in the past. And we have different classifications for different galaxies. There's UGC, PGC, NGC, IC. There's a dozen different classifications for stars and objects in the night sky. So I'm going to open this up completely to questions right now. Who has questions? What would they like to know about or see in the night sky?
John, I thought I saw a couple of questions in the chat.
I'm going through the chat now to see if I can find something. Everything looks good. No, don't have audio, still no audio. We're able to see the moons of Saturn. We did, yes. For the hobbyists, you sure rock it, John. Thanks. Congratulations. Thank you so much. Pretty amazing. For comparison, the sun is 8 light minutes from the Earth, yes. Jupiter is naked eye visible, so is Saturn right now, so is Mars. Phenomenal, would never have gotten this much out of the experience on my own. Thank you. The Andromeda Galaxy is headed our way. Yes, in 7 billion years, we expect to see a complete merge of the Andromeda and Milky Way. And they've already named that, that combination of galaxies called Milkomeda. So
7 billion years?
7.5 billion years from now, it'll be a complete merge.
That's right. That's right. Okay.
Yeah, but at 4.5 billion years, our sun will disappear, so we don't care.
Oh.
Yeah, so we won't even be around in 4.5 billion years for sure, unless we find a way to get off of this place and go to another star system that's newly formed so that we can find a new home. Somebody wanted to go to Jupiter, Juppiter. I was watching another live show this morning. Somebody said, "Oh, can you find God?" So here's what the guy did. This is fun. Let me do this. He goes up here and he types in God, G-O-D. And if we can find anything in the universe, we can find God. Well, we have all kinds of God, something or other, but we don't have any God. Sorry, God doesn't exist in this universe. So that's the outcome of that.
Hey, Dad, can you find Ghost of Jupiter? I think a 30-second exposure might be able to show that.
Absolutely, Ghost of Jupiter. I've got pictures of it. In fact, it doesn't look too exciting, but it's definitely GOST. Ghost of Jupiter Nebula. Now this is a different one. There's Ghost of Jupiter and Ghost of Jupiter Nebula. Ghost of Jupiter Nebula is actually below the horizon right now, so we can't see that. So there's another one that I was thinking that you might be interested in, and that's the Ghost of Merak. No, it's Merak's ghost. What am I saying? There's Merak, and then there's Merak's ghost. So Merak's ghost is actually a galaxy sitting right next to the star Merak's. And I've got pictures of that. So when we look at Merak's ghost, and then we also take a look and see what stars we have. So there's the star of Merak, and then right next to it is Merak's ghost. So this is a challenge for almost anybody that wants to do some long exposure photography. Are you going to be able to see that galaxy sitting next to that sun? And my answer is yes, you can. So I'm going to come over here and look into my lights and go down to, there it is, Merak's ghost. So there's Merak's ghost. That's the galaxy right next to the star Merak. So I'm able to pick it out with this combination. It's just, I was blown away when I realized, hey, I can capture a very dim galaxy next to a very bright star. But Jupiter's ghost, no, that's on the other side.
If you have a picture of Ghost of Jupiter, that'd be cool.
Let me see if I do. And that might be a little challenging for me to see. it will have an NGC number, I'm sure. Let's see if I can find out what that NGC number is. Get rid of that. We're in Jupiter and see what comes up with Ghost. Oh, there it is. So it's NGC 3242. So let me see if I have that one in my list. 3242, we're looking for NGC. Nope, I don't have it. So it would be listed in there. So that's one that I'm going to have to wait for, see when it's going to come up again. It'll be interesting. So go outside and look up. It's really amazing. Yes. Thank you, John. Thank you. Thank you. From Sylvia Brown. Oh, Sylvia Brown was here. Everybody knows Sylvia Brown, right? She's the psychic. I don't think it's the same Sylvia Brown, though. I met her in person one time. She walked up to me, thumped me in the chest right there in the middle and said, "Open up your heart." And I'll have to admit, at that time, I was pretty shut down. I had no idea what being a heartful, soulful person was. I was all in my head, totally in my head at the time. Any other questions, ideas, what to look for? So we got that galaxy. It did
Well,
come in.
how far from that star is Merak's Ghost, the galaxy?
Oh, in terms of angular distance, let's do this. Let's do a measure. And let's draw a line between the two. And it comes out to be, if you can read that, the labels are in the way. So let me get rid of the labels. They're still in the way.
Don't show.
If we went the other way.
How about physical distance?
Well, we would have to find out what the distance of each one of these objects are, and that would determine if we do the get info and come over here to the data and look at the distance. Merak's Ghost is at 9.7 million light years. And then if we just do a search for Merak, oh, come on. Got R's in the wrong place. So there's Merak. So we got that, and it's 197 light years away.
Okay.
So there's a huge
5
gap.
light years. Yeah.
There's a huge gap between the two because this galaxy is not even in our galaxy,
Right.
and this star is in our galaxy. So now when we do that, the distance is, there we go, 9.7 million light years. So that's how far away the galaxy is from Merak, 9.7 million light years.
Not too far.
Yeah, right. just a hop, skip, and a jump.
Can we get a look at any nebulae like in say like around Orion, or I guess we can't see Orion.
Oh, yes, we can. We can see
okay.
Orion. Yeah. So you want to see like, yeah, any one of those objects out there in Orion?
Yeah.
Okay, so let me pull out of this, and we'll go to M42, which is the Orion Nebula.
John,
Yes.
have many of the folks gone outside and seen it with their naked eye?
The Jupiter conjunction?
Yeah.
I'm pretty sure a lot of people have that were able to get there. So now as I'm noticing here, as far as the position of the Orion Nebula, it's almost, it's probably at the point where we won't be able to see it, but we're going to go there anyway. We're going to try to do a go-to Orion's Nebula and see if we can pick off anything, because I think it's right at that hairy edge. It's at 8 degrees above the horizon. And I'm pretty sure that's below the level of my observatory. But not to turn you away, I'm pretty sure what I've got in here, come on, snapshot. These are all snapshots that I took last night. Light, M42. So on December 19th, I took this image. And now we can, oops, come on, get out of the way. Look at that. And that's not in color right there. So that's just the image that I captured on the 19th. And I took 30 images of that. So what we can do here to get color out of that is we can use an application called debayer. And when I do a debayer on that object, and I have to make sure that we're getting the right color combination here. We want RGB and drop it on there. So Jeff, I recognize your voice before I even saw your name on the image up here. Very distinctive to me. So there's the color image of the Orion Nebula. And I've got other images of the Orion Nebula that will make this look sick. But what's unique about this one right here is right there in the middle of that group, there's 4 stars that are fairly close together. 1, 2, 3, 4. These 4 stars are called the trapezium. Each of those stars is actually a double. Now, each of those stars is a double. So we've got a quadruple going here. So there's actually 8 stars here and not just 4. No, there's 16 stars here instead of just 4. So each one of those is a double, like 4 stars in that one group. So 4 times 4 is 16. So we got 16 stars right here, but they shine like they're only 4. So each group is a double and each one of those doubles is a double. It blew my mind when I read that. So let's switch over and show you my M42 that I'm quite proud of. And I'm going to show you the Hubble Nebula first. So this is the Hubble field that shows all the dark area around in here. And then down inside here, there's where the trapezium is. And right up here, you see this elongation of dark cloud plus this one. This is the Running Man Nebula. So he's got his arms outstretched and he's running along, and 2 of his legs. And then there's a bright star right there that kind of hides everything. So let's go back and look at my other image that I have that I took of the Orion Nebula. Here we go. So this is my image that I took. And you can see the Running Man up here quite clearly. And all of this area in here, I could recolor this completely and make it look more purplish. But this is what I wound up with. And I thought, nah, I'm happy with that. But I have other images that I've taken. This one isn't mine for sure. That's somebody else that I copied from. And I just grabbed their images and I think I like them. And then this is one that I definitely took a long time ago using a much smaller resolution camera. It shows you the grouping of the trapezium in there quite well. What I did at one time is I took a bunch of images that I took at different exposures. I started at 2 seconds and went all the way up to 60 seconds in steps. And I combined all those images. I like to think it's this one here, but I don't think it is. I'm not sure what happened to that one image, but it's not showing up in here. No. So I've got a combined stacked images of the Orion Nebula. So let's see what happened to our nebula over here. Let's drop this down to 10 seconds and see what's showing up. There you go. There's the Orion Nebula. And you'll notice the grouping of stars in here. Now, this application, when it does this capture like this, it does an automatic stretch and debayer, which is why the colors look pretty good the way they come out. And you can just barely make out the running man over here. It's not all that clear. So even at 10-second exposure, we're getting a pretty good thing. I would have to go up to a 5-minute exposure in order to see the billowing cloud that we have around the outside of this. So there we go. At 8 degrees above the horizon, I'm still able to pick it off. It's still above my borderline. So my borderline must be a little bit below that. I think if I went out there, maybe half of the telescope would be occluded, but we're still getting the image. So Orion's shield is up there. So we have, oh, that would be the Horsehead Nebula right there. Well, it's actually below further. All right, so we're not going to be able to see the Horsehead Nebula. That's definitely below the horizon, but it says 10 degrees. Oh, what the heck? Let's give it a shot. Let's go there. And we're waiting for it to settle. Looks like it's settled. Okay, let's take a 10-second exposure. I do not see it, guys. It's a pretty dim object by comparison. Let's try 30 seconds. Yep.
Once you get done with this, Joan Brown, she'd probably like us to fly out of our solar system and then outside of our galaxy. She wants to take a look at our galaxy from the outside.
Okay, we can give that a try as soon as I put on my jumpsuit. I have to be in my jumpsuit to jump out that high.
Well, we got Sky Safari. We'll use it.
Oh, yeah. Yeah, so using Sky Safari, which is interesting, we can actually go out to M31, which is the Andromeda Galaxy. And once we have it picked off like that, then we can say, let's orbit that sucker. So notice it's right there on the zenith. So it's just crossed over, or it's about to cross over. Which one is it going to right now? It's about to cross over the zenith. So at this point right here, my telescope is pointing almost straight up because there's the zenith right there. And in just a few minutes, the telescope is going to cross over the zenith, at which point in time it's going to get to about here and stop, because I've got a hard limit in there that says 5 degrees past the zenith, don't go any further, just do a hard stop and quit. So then I would have to flip the telescope around, and instead of looking for the Andromeda Galaxy from the east, I would have to look for the Andromeda Galaxy from the west. And then I could start tracking again as it continues moving westward. Now, when you do that, the camera is actually going to be turned upside down. So we have a 180-degree view of it from the other side. So if I take a picture of it from this side and then take another picture from that side, the two pictures are going to be 180 degrees out. Knowing that, I could actually take the group of photos that are 180 degrees out, flip them, and then stack them up with the others. There are some software out there that will do that for you automatically. It can recognize that the two images are 180 degrees out and do the flip and get them to line up. So here's another issue that I want to point out. Notice the Andromeda Galaxy is right up there. So there we have it. There's the Andromeda Galaxy. It's pretty much out of the field of view on the guide scope. That's because the guide scope is not perfectly centered with the main telescope. So I would have to do an adjustment on the guide scope to get it to come in. But there's a lot of flop and play in the guide scope. If I move the telescope in one direction, the guide scope is pretty close. Move it into another direction, the guide scope is out. So something's going on, and there's a flip-flop going on inside there. So we're only looking at the central bulge of that galaxy. Keep in mind, this is a ½ degree right there. So when I take a look at this, we're looking right down into the throat of the galaxy. And here's the companion galaxy, M110. I think that might be M110 because M32 is pretty close by in there. So if I wanted to play around with this and bring it more to the center, I think I would have to go this direction and then definitely in this direction. And let's take another 10 seconds and see if I came anywhere close. Not too bad, went in the wrong direction. So let's go a lot in that direction. Yep, so we're pretty close to center here. And again, we're only looking at a very small portion of the entire galaxy. And for a 10-second exposure, we're looking pretty much inside the throat of that galaxy. If I were to turn this up to, say, 5-minute exposure, we'll be able to see the dust lanes around the outside edge a little clearer. And might even show up M32 that's really close by. Somewhere in there, it's going to be hugging it pretty close. I would need to reconfigure my telescope for the wide field of view in order to pick up the whole thing side to side. And then it would blow out the core from the inside. So this is where we go into the multi-exposure. A bunch of 10 seconds, a bunch of 20, 30, 40, all the way up to 5 minutes. And just stack those together and come out with a pretty clean and decent image. But for a one-shot color, high definition, seeing lots of stars around. These stars that you see here are in our galaxy. We cannot see the individual stars in that galaxy. All we see is just this fuzzy blob of light of these stars that are compact so close together that it just looks like a haze. So everything that you see here is a star in our galaxy. Anything else? Yeah, we can only see our galaxy from the inside, not as a whole. And not only that, we can only see what's on our side of the galaxy. We can't see what's on the other side of the galaxy. Now, if we took a look at Uranus, the planet, can we even see it? So let me see if Uranus is even possible, because at one point I think it was. Yes, Uranus is possible. So what would it look like if we went to see Uranus? So let's go to Uranus. Now notice it's just a dot. So I'm pretty sure that when we take a photo of this, we're going to see a dot among a bunch of other dots. And now in a good color photograph, what we'll be able to pick out of that is like maybe we'll see a little blue haze for that particular star color, and that will identify it as the star. So let's go back over here, take another 10-second image, see what comes out of this one. Now, because the Andromeda Galaxy was out of view, we're probably going to expect to see Uranus is going to be one of the dots up in this area. Thought I took a picture. Okay, so that might be it. That could very well be Uranus right there. Now, the way we can know that is to actually bring this down to a 1-second exposure, go into a loop, and then let's recenter this so we can get that star pretty much in the center. And then once we've got it pretty much in the center, we can do a plate solve on it to find out what it is. And if the numbers for the plate solving come up to match the numbers for what the, oh, there we go, there's the center.
It does appear to have that bluish haze.
Yeah, around the outside edge. I'm teasing it in, just one tap at a time. That's close enough for me. I don't want to tap it anymore. I can actually go down to the guide speed and bring it down that way. Get it perfectly centered. But I'm going to go ahead and do a plate solve on this and see what it comes up with. It's working pretty hard. It's taking an awful lot of exposures. I'm not sure what it's doing there.
Hey, John, can you hear me?
Yep.
Yeah, this is Edwin EJ. The reason I wanted to see that was that a couple years ago, I was trying to look at Uranus from my backyard, and I just barely got a glimmer of blue.
Yeah.
I really couldn't see it, but just, I just barely, like maybe from my side vision, all blue.
Yep.
And I was thinking that I wasn't sure whether I saw it or not. It wasn't like I really
so as you notice here, when I turn off the stretching mode here, we don't see any stars in here at 1 second. And this is supposed to be up to a 6-second exposure, but I see that it's only doing 1 second exposures. Oh, I know why it's not doing plate solve. I had this turned on. Let's go back to plate solve. Sorry about that. So now I stop this sucker. Now we can do a plate solve. I was waiting for something that was never going to happen. So it's doing a 6-second exposure now. And then it's going to take a look at that and try to match it up with what it thinks it knows about that area of the sky. And it found it. So it found it at 21. No, this is the one that found it. So this is the time now. So 2:17:55. And the other one was 0:12:2. So let's see how that matches up with what we think it ought to be over here. So looking at this, it says 2:19, so 2:17, not that much different. And then 13:24, and it's supposed to be 0:12. So this is like 0:24, if you want to look at it from that perspective. So quite a bit off on that. So where would 0:12 be on this? I would have to disconnect from this and watch up here, and we go to different coordinates. We need the equatorial coordinates. Monitor this to see if we can get to, see, we thought Uranus was here. That's 0:19:3. That's pretty close to 2:17. We went to 2:32. So we're down in here someplace. So we're not even close to Uranus. We're down in this area. So that's not Uranus that we were looking at. It's got to be some other star. What star would that be? Show stars. I don't see any stars in that area. Okay. See, not a galaxies. Yeah, there are a few stars. Here's a star that it might be. So let's put that in the center. No, that's the wrong one.
It could be the date. I think the date said.
So right in there, this area here is where that bright star is supposed to be that we saw. And 2017, we're off a little bit there too. We want to be on 217. And then 0, 12. So, nope, there's no star in that area where we calculated the telescope is looking at.
The date, that maybe the date. Did I see the date as the 18th?
No, we're 12/21 is where we're at for the date.
It came up before showing 18.
Huh.
But not now, yeah.
Okay. So let's come back to Uranus. Let's get Uranus in there. Oh, connecting. Go to. And then take another picture. Well, we're still centered on that very same star, whatever that star happens to be. And according to the detail that we get out of here, it's supposed to be 2, 19, and 1324. So let's go to 1324 and see 219 is where we want to go. 219, 0. And then 1324. So let's put those coordinates in as a forced direction using telescope controls. 2, 19, 0. And then for that one, we want 13, 24, 0. And slew. Let's see what we get out of that. I'm waiting for it to finish. So it's settling. Take a 10-second exposure and see what pops up. Finishing the exposure now. So somewhere in here, maybe, or maybe even that. I would be very surprised if it was that. Notice we're getting a little bit of elongation in the stars here. It's not perfectly centered, so this indicates to me that I have to go and try to pump this up a little bit and move it in, because I know it's going to change over time.
So has Saturn and Jupiter dropped below the top of your observatory
Right,
now?
definitely.
Would we be able to get a look at M74? It's about a magnitude 9 plus ish, and I don't know what the exposure would need to be for that.
M74. Spiral Galaxy. Not too far away from Uranus. Yes. And that would be probably a 30-second exposure to get good detail out of it. And we'll look at the info on this. And it says, okay, the magnitude is 9.3 or 9.0. So yeah, we could get a 10-second exposure on that easily. But let's see where we at with this one. Oh yeah, so just bumping that up a little bit gave me a little tighter on that as far as the exposure is concerned. And that might also help for doing a plate solving. So let's do another plate solve to see where we're at. We're at 219.0, which is where we want to be, and 1323.59, which is where we want to be, because that's where I told it to go. And those are the coordinates that we picked off from here for that particular site, for Uranus. Let's go back to Uranus. So 219.1, 219.0, same, 1324. Yeah, so I'm feeling confident that what we're looking at here in this field of view, in the center, is one of these dots. It's going to be Uranus. And it's, it doesn't look like anything, does it? You would expect to see something more prominent, like maybe that. And when I look back over here inside this field of view, notice there is a bright star in that field of view. So yeah, so we are seeing that bright star inside here. So, and as far as the orientation is concerned, we're looking, it's, yeah, let me disconnect here so I can move the map around. So if Uranus were centered, the bright star would be up there. And what we're seeing here, bright star is there, so maybe that would be Uranus. It's just off center a little bit.
I agree with that, yeah.
Yep. So that would be Uranus, as opposed to this other one that we were looking at. But this looks like it has moons around it, doesn't it?
It does.
I don't think Uranus has any moons.
Can you
Yes, it does. Yes, it does. It's got quite a few moons. And that bright star that we were seeing over here, there's no, so good Lord, people, I'm pretty sure that what we're looking at here is this combination. That's got to be Uranus.
Down in this, with this
Yeah,
picture.
That's right. That's right. That's right. So we're seeing the moons of Uranus, people. blows me away.
That's fantastic.
Totally blows me away, guys. I've never seen anything like this before. Not visually anyway. So if I were to recenter that and then get, do a plate solve to find out what it thinks it's looking at, that should be the thing right there. So I'm taking this down to 0.5 and then doing a loop-to-loop on this thing. Let's see what's going to happen to this object when we do that. And then turning on our, so we want to go to here. So there's the center. So we're going to bring that from there to there. So put it in centering mode. Let's see if we're going in the right direction. Yep, we are. Just needs to be nudged a little bit. Okay, let's do a plate solve on that. So turn this off. Do a plate solve. Let's see what new numbers we come up with. See how they compare with the previous numbers. Oh, gotta get it started.
What are we looking at here?
As far as this whole thing, we're looking at the feature inside NINA. NINA is the name of the application, N-I-N-A, or N.I.N.A. Something to do with another imaging, something or other, I can't remember. So now the new images that we got, instead of 219, it came up to 21755, which was my previous measurement. Literally exactly on, that's what Sky Safari said it should be, and 1318 instead of 1324. 131818.
Well, I think you nailed it.
I think I nailed it. I sure did. That's a win for me. You know what I'm going to do? I'm going to take a snapshot of this. I'm going to turn this up to like 20 seconds and make sure that my snapshot is turned on and take an image. So I have a record that I dooted it. And then when this is done, we'll move over to M74. Take a look at a galaxy there.
Mm-hmm. Insert planet name joke here.
Is there a what?
Insert planet name joke here.
Oh, I see. Yeah. All right, so looking over here in my thing, it's under the snapshots, 1021. It's this guy, and I'm going to rename that Uranus. How about that? And then if I double click on it, it's going to show me this, and then we do an automatic slow, and there it is. And we can zoom in on that. Look at that.
I think whoever asked for that, you need to send them a photo.
Yeah, I think I need to send that person a photo, and with a blue star on it too, or a gold star. You want a blue star or gold star? Silver star. I don't know. Name your star.
So which one of the dots around there do you think are moons?
All of them, literally, all of these, all four of those, and maybe even this one. So let's take a look back over here to this and zoom in on it. So as you can see, the arrangement of moons that we have in here, there's these and then those. So, very definitely, we're looking at kind of like a crosshair on that.
Mm-hmm.
So, yeah, so all of these and very likely this one, but definitely those four. Because
And the one just below your cursor too.
the one just below. Oh,
Looks like you might have titanium there too.
This one here?
Yes.
Yeah.
Yeah, that's a possible. Yeah.
Yeah, according to Sky Safari, that looked like it was one of them that made that cross.
Yeah. Yeah. Okay. So this is cool. I have never seen a good image of Uranus. I'm blown away. Thanks. And for a single 20-second shot.
It looked like it was pretty near the zenith, so I thought we might get lucky.
Yeah.
Well, and we're so close to M74. It's not going to be a far jump for your camera.
No,
or your telescope,
and it'll still be in sync.
And I'm hoping you'll get a really good shot of this pinwheel.
Oh, come on.
So after M74, I'd like to take a look at Mars, and there won't be any question about whether we have the right object, and we can compare.
Yeah.
No, we can compare with the solar.
It'll be pretty yes.
With the ephemeris.
Okay. Now, you'll notice all of these pictures that I'm taking are without any guiding. I have not turned my guide scope and not turned on the software for guiding. So as far as the scope tracking, even up to 20 seconds, 30 seconds with no problem. If I were to go up to like 5 minutes, we would see star trails. So let's leave that on 20 seconds and see what pops up. Oh, you know what yeah, okay, I did it, yeah. So when I did the plate solving, it also did a sync to the telescope to say, here's where we are at. We are at this location. So moving to another location, the scope, that close by, we should be dead center for this new object. Well, where is it? Did it not move? Did it not go there? According to this, it went there. Oh, we weren't connected.
Didn't you disconnect at one point?
I was disconnected. Okay, so now we can do a go to. Sorry about that, guys. So I got 2 snapshots of that. Okay, good.
Well, if you give the first one away, you keep the other one for yourself.
Oh yeah, yeah.
So John, what kind of magnification can you use on your scope on a good night? I'm sure it's viewing limited rather than diffraction limited, right?
No, there's a diffraction limit on this telescope. I can get up to about 840 magnification on it.
Oh, that's the diffraction limit?
Yep.
Okay. And you actually have good enough seeing to use that?
Where I'm at, I can push it. I can definitely get up close to 800 if I have the right combination of lens and eyepiece and all that sort of stuff. So with the camera that I've got, I would have to really fudge around with different focal reducers and Barlows in order to get it. So it depends. It would be a lot easier if I use eyepieces for that magnification, because I don't think, well, let's see, that's not quite true. Because what I can do is I can actually play around with the different, let me make this full screen here. I can play around with the telescope display and say, instead of using this camera, let's use a different camera. And the camera that we would want to use would be, why don't I see it in there? Oh, yeah, this one, the infinity. So notice the little blue rectangle now got really, really tight. So if I put the infinity telescope on there, I can really get into a tight view, like less than 2/10 of a degree. So that would be a possibility. And it's a more sensitive telescope. Also, with the infinity camera, we could see a better view of that galaxy. Right now, this is the field of view we see with this camera. So we're going to see a pretty small galaxy in there. And let's hope we don't have to recenter. Look at that, dead center. It's right there in it.
I need a good 60-second exposure of this.
Do you want to do that? 60 seconds?
Well, I hate to waste people's time, but it's
You're not wasting my time.
Okay, let's do it.
We've been here for over 2 hours. I think we can hang out for 60 seconds.
Okay. And it would also help to zoom in on it a little bit. Okay, I need the guide for that. Definitely I need the guide. So 60 seconds going to have to, that's going to require guiding. So let's pick a star for guiding and guide on it.
Just what we're looking at now looks phenomenal.
Yeah, it does. But I'm pretty sure, notice the little streaking that we got in here? So the telescope might have still been moving when I took the image. So we're going to see a little streak on this next image, but then I'll shoot it one more time because we're guiding now, and we're going to make sure that it's going to stay on center.
So John, are you directly connected to your telescope, or do you have a Wi-Fi connection to it?
It's a Wi-Fi connection.
Okay.
Now there's this entire view that you're seeing here is a computer in the telescope observatory, which is directly connected to the camera and the telescope. And then I'm Wi-Fi connected from this computer in the house to that computer in the observatory. So as far as connection to the telescope from the computer, it's a direct connection.
Yeah, it's a
what
USB.
we're seeing here is a, oh, look, we got a satellite streak through that one.
It's probably a Starlink.
Yeah, so I'm going to have to take another 60-second exposure. And even at 60 seconds, it's still not enough. We would have to go to 5 minutes for this guy to get it in really good.
Well, you don't want a picture of the satellite streak?
No.
Was it one of those Starlink satellites?
Yeah. That's
Notice it. We didn't get the whole streak, though. We only got a portion of it.
Well, I think that's a conversation piece anyway.
Thank you. Eight seconds to go. Yeah, so I'm using several pieces of software in combination here.
Yeah.
It's just, and the Nina software that I'm using right now to capture the images, to move to a start, to do the plate solving. I could even do the autofocus at this point, but the autofocus takes up to 2 to 3 minutes to complete. Now, did the telescope jitter? Let's zoom in and see what we got for pretty good focus.
Yeah.
A little elliptical, but
yeah, just a little.
Really good. That's really neat.
Yeah.
So if you wanted to sit through an autofocus to see what that looks like, what we're going to wind up with is a V-shaped curve, and it's going to calculate the difference between out of focus at either end and the inner focus. You want to do that?
Let's go. Sure.
Start the autofocus.
I've still got 15 minutes of battery life on my phone. I can.
Oh, good.
I'll have to switch over to my desktop here. Right now, I've got it mirrored to my television screen in the living room from my phone. That's how I'm participating.
You can plug it in, Ed. You can plug it in.
Thank you, John. My wife's going to throw my dinner out if I don't get over there.
I was going to try to use.
This was really
sorry, go ahead.
much. Thank you.
He's recording too, so that we'll be able to watch this playback.
I was going to try to use the web browser on my Samsung, but I didn't want to type in the Zoom link.
Oh, no. So notice from the first focus image that it took to the second one, it bloomed. So that's like crazy. So let's watch the donuts as it does this. So I'm going to switch over to the image mode, and you see the star is really, really out of focus here. And it's going to make it sharper and sharper into focus, and then go in the other direction to out of focus. And then it's going to calculate the difference between the two, like in a V curve, and come up with something. Now, when we're doing it with galaxies, it gets to be a little more complicated because the galaxy actually interferes with the plate solving a little bit. I wish I could control how many stars to use, how many bright, I think I can, how many bright stars to use for autofocus. So if I limit it to like the 10 brightest stars, then that's going to pretty much eliminate the galaxy in the center. But right now, I think the way it's running is like the 50 brightest stars, and it might pick up some of those in the galaxy, which are diffuse. They're not actually stars. So it can get really confused as to what to do. Now we're starting to get a trend line here. So two things are going to be happening. We get a trend line on either side, which is going to form a V, and then we get a parabola curve out of this. So the software is actually going to do a calculation between the trend line and the parabola and kind of like crosshair that thing and say, here's the best focus point. And we started out with a focus point of 23,995. So let's see what it's going to wind up with for the final calculation. So now we're starting to go up a little bit.
So what's on the vertical axis there?
This is actually what we call half width diameter. So when you look at a star half flux diameter. Okay. When you look at a star and you zoom in on it, it's going to have a width to it.
Okay.
And what it's doing is taking half of that width and saying, okay, this is the diameter of the star. So when it gets to a point that says, okay, half width in this one direction, or half flux in one direction versus half flux in the other, and then it does a calculation between the two. Now, if you'll notice that it doesn't, this inner dark area isn't quite centered inside the outer ring. And that tells me that the scope isn't perfectly collimated. So because it's not perfectly collimated, I can never get a perfect focus. It's always going to be a slight teardrop when I focus it. So I got to spend time out there just fine tweaking the knobs on that secondary until I get that tuned in. And it takes 10, 15, 20 minutes of tweaking to get that. If I had an artificial star to work with, which would give me a more defined image to play with, then I could get it done a lot faster. But because I'm working with dim stars, bright stars, and all that sort of stuff, it gets complicated. So now we're moving further out of focus. So that means we're moving up the curve. So notice here's our V-shaped curve and our parabola. So somewhere in this area is going to be our perfect focus, 24 something, 2410, 2014. I'm going to call it 24014. So that's quite a bit off of what we were originally. So it's doing the final calculation.
John, how long have you been using this equipment and this particular software package? Has this been something that's been user-friendly in terms of learning and teaching yourself? Because it's very sophisticated.
Okay, this software package right here?
Yes, sir.
1 week.
You're kidding.
1 week.
And you got this proficient in 1 week with this software?
In 1 week.
I'm flabbergasted.
You might be able to contribute that to my IQ. I don't know. I've been told I'm a genius level, but
well, you are a brilliant man, that's to be sure. And you've had your equipment for quite some time, right, John?
I've had this telescope for 4 years now. For going on 5 years. And the camera I've had for going on 4
If
years.
you don't count the time that it's been in the shop.
Yeah, you're exactly. That telescope that I showed the picture of at the beginning, I dropped it on the ground.
Oh,
and
no.
and it shattered, literally. Brand new, the telescope cost $6,000.
Wow.
When I got the bill for the rework, it was $5,900.
Oh my gosh.
But the rebuilt actually turned out to be better than buying a new one to replace it.
I think I was upset about dropping my iPad.
Yeah. And people, you know, they were thinking, but you must have been out of your mind when that thing hit the ground. I says, no, when it hit the ground and I heard the glass shatter, I just said, oops. That was it. I could not allow myself to go into a tantrum over it. It's just like, it wasn't worth it. You know, it happened. And it was my fault that it happened. I was trying to rebalance or move the telescope on the rail back and forth instead of being smart about it. I kept loosening up the clutch and it wouldn't move. I kept loosening the clutch, it would move. I loosened the clutch and it fell off. And it's too heavy for me to hold on to. If I had tried to hold on to it, I would have literally been in the hospital trying to keep that from hitting the ground. So there it came up and it said 23,990, and we were originally at 23,995. So I was only a tiny bit off.
I would call that a really close fit. So you
Yeah.
did good, John.
So now if
why wasn't it at the very bottom of that parabola, which was like about just slightly above 24,000?
Yeah, I was thinking the same thing too. You know, it seemed to me like it should have been right in this area here, which would have been above 24,000, but it decided to go off to this side. So this is what it thinks should be the correct based on all these others. Now, myself, I'm going to put in 24,050. I'm going to try to move to that side of the curve and see what happens, because we can see right now. Whoops.
Not 24,005.
Yeah. So we can see right now we've got this image. So I'm going to move it into 24,005. We'll try that and move it. And then take another 6 seconds to match up with what it did. And see if that's going to get any tighter. Tighter.
Mm-hmm.
Yep, definitely works out better.
So yeah, now we can take a good shot at M74, right?
That's right. Yes.
Well, actually, you did get the shot. You just resumed in.
But not, yeah, it wasn't this tight of a focus. So let's go back up to 60 seconds for that.
Looks like you have some ripple in your image there.
That's banding, and it's caused by the camera.
Mm-hmm.
And there are adjustments that you can get rid of that banding. But here's the thing, the banding disappears if you take a long enough exposure.
Oh, okay.
So if I were to do like a 5 or 10 minute exposure, that banding would disappear. And the other way to deal with that is to combine it with what we call flats and darks. So the flats and darks will have the same banding in it, but at a different resolution and all that, so that it'll subtract out. And then there's—
Is that just the scan rate on the sensor then that's doing
it? Something of that nature. And they know about it, but there are other cameras that I could have purchased had I known about this banding in this camera. But if I use a different, there's another application that I could be using that I had been using for a long time, and it's called SharpCap. So SharpCap is another application that I've been using for like couple of years, maybe 3 years now. And this is the one that I've been playing with the most. And it has an adjustment in it in the tools area off to the side here for reducing the banding. And it's complex, and I've tried to tweak with it, and it just never really got it out. But what I've noticed is a longer exposure makes it go away. So for this one here, if I say I'm using this particular camera, then it comes out here and it says, all right, let's load up a profile. So this is a light profile, so we got that. So now it's going to take a 2-second exposure, and it's going to automatically, with this software here, it's automatically going to go in and make my temperature down to -15, which is where I like it. I can adjust the gain and the exposure for this one. I can adjust the offset. So I get a little more control. And also in this one, I have pre-processing controls. I can subtract the darks and the flats built into that. And then there's image control. I can adjust the red, green, and blue images on this one, and the brightness and contrast and gamma. So I have more control over the image with this one. In addition,
so
it has.
Go to the other software.
Huh?
What made you decide to use the other software?
Because the other software has autofocus and plate solving. There's no autofocus on this software.
I see.
And focusing has been one of my biggest problems. I'll start taking a series of images with this one and say I want 30 images. If I focus at the beginning, it's out of focus at the end. So with Nina, it'll focus every 10 frames. And then I know by the time we get to the end, it's going to be still focused. Also the plate solving. With the plate solving, I can tell it where I want it to go. And with the plate solving, it'll perfectly center it. Whereas with this software here, I have to play around and nudge it to get it centered. So Nina has more control over the telescope and less control over the camera. Oh, we got a blurred image.
Yeah.
That didn't help us at all. Why would that be? Oh, we're not guiding. No, we are. Look at that.
Well, that's tracking though. That's tracking those.
But no, the guiding is going to lock it in no matter what. Oh, but I don't see any guiding result here.
Yeah.
There's something else locking out the.
There's something else that's blocking this from working then. So even though this may appear to be guiding, it's not showing up in my thing here that it was guiding. All right, so let's play this game. We're going to take. Oh man, go back to Carte du Ciel, put in M74, click on it, and then come back over here to the framing, get the coordinates, and match them up with what we think it should have been. I don't know what it should have been, but there we are. And then I'm going to add this to a sequence and do a simple sequence. And now here's the simple sequence. And we start the guiding, make sure it's on. We could center the target and we could slew to the target, but we're happy with the position where it's at, so we're not going to do any of that. So total of 1 image, and for 60 seconds. It's a light. We're not going to dither for 1 image, and we're going to turn the gain down to 1. We could use the gain of 3200, but I'm going to leave that, and the offset, we'll leave that one alone. And then over here, I'm going to do a full stop on this and make sure that in our equipment settings that the guide is turned on and it says disconnect, so we know we're turned on. Oh, this telescope, where's the guide? Right here. Disconnect, so we're definitely connected. All right, so now we come over to our sequencer and start.
John, thank you again. I have to punch, but thank you so much for a wonderful evening.
You're welcome.
You really rocked it out of the ballpark, sir.
Oh, good. So we're doing exposure now for 60 seconds. And supposedly we're saying we're guiding. Come back over here to our imaging, and hopefully we won't have any more jitter left in this thing. But I still don't see it guiding here. We're supposed to see the guiding, and I'm not seeing it. This is the first time I have not seen it guiding in here. And the guide has been very, very good in the past. I mean, just like plus or minus a half a pixel. You just see it jitter right down here in the middle. And that's, to me, that's excellent. I think several years ago, I was watching it just do this kind of thing back and forth, hunting, you know, trying to find a center point, never finding it. And the other thing, this needs to go to 3 seconds for a better guide. I don't like that pattern at all. It doesn't look right. You see anything that looks like a galaxy in here? I don't.
No, I'm not tracking anything there.
I'm
trying to match up the stars that I do see to what I'm seeing in your other image. It seems like it would be right underneath that crosshair.
Got total black. You know why I got total black? I'm down below my field of view. I have bottomed out. I'm looking into my wall. Can't be looking into the wall. Let's go back to, oh, crossover. We hit the crossover point. It's like M74 has just see the green line moving. It's getting closer and closer and closer. So we're pointing almost straight up right now. I would have to quit, flip the image, go back around the other side, make sure that that we could see it. And the best way to do that is to find an object. I don't like to do a peer flip. I've never done a peer flip. There's a way to do an automatic peer flip, but I'm not trusting that. So we want to find something over here and go to that, but we have to turn off the guiding. Yeah, it's off. So now we'll do a go to get to that star. So now it's going to go all the way around and come back to this. And there's Mars. He wanted to take a look at Mars. We can, yeah, Mars is about ready to cross over too. Now, I'm noticing something that isn't quite right here. There we go. Now, streaking stars, as long as I'm seeing something moving here, because these little dots here, those are what we call hot pixels on the camera. We can't guide on those. We have to have a bright enough star that overrides what these hot pixels are. And if we don't see a bright enough star, then we can't guide on it. So that's the star that we just did a go-to on. So just going down to a 1 second here and doing a quick capture. We should see it in here. Why is it taking so long? Come on, wake up.
Long 1 second.
That is a long 1 second.
Is it still set for 60 seconds by chance?
No, it's set for 1 second.
Okay. I got you.
And we got the X in here, which says cancel, cancel. So, and now I know I'm guiding on that star. I mean, so that's something reality. Well, it looks like we're hung. I'm still able to do some mediocre control. Oh, I think I know what the problem is. Let's turn this guy off. We had a conflict between the two pieces of software.
It's too bad they don't communicate with each other to let you know that.
Yeah. The other pieces of software work well together, like Sequence Generator Pro and SharpCap Pro. I can have both of those running at the same time and both taking pictures at the same time. So it's like, but Nina doesn't work well with SharpCap. So I'm either going to be using, disconnect Nina if I'm going to use SharpCap, disconnect SharpCap if I'm going to use Nina. So
Okay, well, John, excuse me, I'm going to have to drop off now. I really appreciate this masterclass and how to run a telescope with all this automation. So thank you very much.
You're welcome.
I captured a whole bunch of web pages for me to do some exploration and see whether I can get my old Meade Classic, LX200 Classic working with it.
All right.
So we'll see. Thank you.
You're welcome. So now I'll go to 74. And 74 is coming off in this direction, so we know we're going to be safe. And a quick 1 second image just to make sure we got something in line. It's going to be pretty close to this area.
Yep, starting to look familiar.
Huh. Nothing showed up, right? Let's go to 10. And it's also guide. It's looking at my hot pixels again. What is going on? Do we have clouds that are getting in the way here? Because the only thing that's going to show these hot pixels like that is if there's something covering up the telescope, the guide scope. I must have got clouded out. And that's not right. Let me go over here to my weather station and see what my weather station is doing. Wind speed, humidity. I don't see any humidity, high humidity. No, I don't see anything as far as cloud cover. It doesn't give me any pictures on. But this is disturbing that I'm only seeing hot pixels.
I think you had to go to
I'm at 3 seconds. I mean, this is what I normally go to for any of my guiding.
But this was a magnitude 9. Are you gonna have to do 10 or longer just to see?
This is absolutely crazy. I'm getting more contrast, but I'm not getting anything that looks like real stars. And it's still picking that same hot pixel to guide on. So I know that's not right. So something has literally covered up my telescope.
Could it
And
be?
I'm not getting anything over here either. Even at 10 seconds, there's nothing showing up here.
So you were pointing pretty much straight up.
Yeah.
Could it be some wires that got pulled loose?
No, I have monitored that too closely. There's, okay, so there's the galaxy at 10 seconds. But I'm not going to be able to do any guiding if I don't see any guide stars over here. And not only that, if it's not showing up on this guide, then that's not going to help me any. So let me do this. I'm going to shut this guy down and then start it up again from over here to see what's going to happen. So let's disconnect everything, shut it down, and we'll leave that one alone. So I'm going to come back over here to equipment and go to guide, disconnect. It says we're disconnected. PhD2. But nothing, come on. Okay, so it brings this up. We're happy with that. Guider connected, good. So it thinks we're happy. So even at 10 seconds, I'm not seeing anything. Well, something's showing up. But I really want to do this at 3 seconds. So if we trust that, that says that's a star. And okay. So then go back over to my picture. And we go into sequencing. And let's do the offset 1. Let's go ahead and capture that. So if we follow the sequence as it goes through, go on, start. It's not starting the sequence. Why isn't it starting the sequence?
Is there a way to pick a different guide star?
Manually, yeah. I can go over here and say, pick that one and then guide on it. But it's, as far as I'm concerned, it's guiding on a hot pixel. That's what it looks like to me anyway. Because I'm familiar with this arrangement for hot pixels. And when I click on start here, another net. So let's do the hard knocks. Let's shut everything down, including closing the application and starting it up again in case there's something messed up in the application at this point. I know last night when I was playing around with all this, I lost connection to my computer completely. Couldn't do anything. Okay, so we've turned everything off. We quit the application. We don't need to worry about this. I'll just start Nina up again. No, this appearance, it's not right. There's probably not enough bright stars in the area for us to pick out something that looks like what it should be. Come on, Nina, I thought guess I didn't. There we go.
What I'm looking at in Sky Safari and what I see in your guide software, those look like they're lining up. It looks like it's matched up.
Okay. All right, so now we can turn on everything piecemeal, go right down the line. Next one is the focuser. Next one is the telescope. Then the guider. And the weather. And then look at the sequencer. I've got to literally come over here back to this. What did we have? We have M74. Yeah, it was in there. So I'm going to add that to the target sequence as soon as it finishes up here. Because I've even done this manually. You know, I've gone over to the sequencing, imaging, come over here, turn the guiding on, and I could see it guiding. So if I pick a star, it keeps picking on that one. And I don't see anything coming out of this. Oh, there we go. There we go. So it's
Yeah,
guiding.
I would definitely, I definitely think that is one of the stars that I am tracking in.
Now, when I go into a really tight vertical, this is a straight line. I never get a straight line. It's always going to be the blue and the red are going to wiggle. And they're going to be wiggling within an area between here and here. And that is just too friggin' tight for me to believe that I'm tracking a real star.
Well, you've done some other adjustments to get focused and.
Not since the last time I worked on this. That tells me I'm not really guiding on a star. But anyway, let's give it a shot. If it's actually working, then what we can do is we'll try a 60-second image to start with and see if it got any star trails without doing the sequencing on this, because this is supposed to work. I mean, if this is real, see, now we're starting to get some fluctuations in here. This is what indicates to me that we may be actually tracking a star. I have never seen it this tight before.
So again, we're pointing straight up. Is it that your camera is rotating more than it's slewing left or right?
Yeah. It's actually, no, the camera's not rotating. It's just the telescope is actually, it's leaning over.
Gotcha. How long does that process take?
There it is. And when we zoom in, there's no star trails.
And so now you can do a good 60-second.
That is a 60-second image.
Oh, that is. Okay. Let's get that pinwheel in there. Let's see.
So,
that's going to be so cool.
all right. So now,
oh my gosh,
it's not perfectly centered, but I don't think we care about that, right?
Right.
Okay. So let's do the save, and let's do another 60-second, unless you want to go to 120.
I've got time.
All
yeah, I've got plenty of time. You're down to about 4 participants, including yourself.
Yeah. So I see the other 3. That's JB and Steve and you.
Yes, sir.
All right, so we're doing 122nd. We're guiding exceptionally well. I've never, ever seen it guide this tight in my entire life. Normally what I will see is like red blips going up and down, and I don't see any red blips on this thing at all. And we're plus or minus 1 degree, so we're well within an, you know, like, and that's pixels. So if we do the arc seconds, so there's the arc second. So let's go back up to this. We're literally plus or minus 1 arc second on average. Now, a plus or minus 1 arc second, that's well within the actually bare minimum of what this telescope is capable of. I'm super impressed. Okay, we're at 85 seconds. I mean, even this, I'm just super impressed with this guiding. So much so, I'm going to take a screenshot of it because I can hardly believe my eyes.
Are there other like configuration settings or adjustments that you can take from that, or is it just you have to tweak almost every time you turn it on?
For what? To get what in?
To dial into this, you know, just how spot on you are right now.
I haven't done anything, literally done nothing.
Well, we did the focusing, right?
We did the focus, but that doesn't affect the focusing of the guide scope. Okay. So the guide scope is a different. The guide scope is totally different. No, I didn't change any calibration. Nothing. Okay.
Well, I thought you did some other guide star calibration earlier.
Oh, 2 weeks ago, I did a guide star guide calibration, and that improved it tenfold. I mean, I was getting plus or minus 2 to 3 degrees change in this. And when I was in the unit pixels here, I would see massive swings with this on the plus or minus 4. It was just bottoming out, just massive swings. And now I'm seeing almost nothing. It just blows me away. I'm not seeing any real changes happening here. It's like the telescope is guiding itself. It doesn't need PhD too.
Yeah, so that 120-second exposure should be done by now, right?
It is. It's done. So this is what we have.
Yeah, I hadn't noticed any change either. That looks good. That is awesome. That's really awesome. That is really awesome.
So there you are. You got your spiral galaxy. And now there's a little bit of star trail in this. Notice there's their elongation. And yeah. I have taken 5-minute exposures with absolutely no elongation. So again, that's kind of makes me think there's something really wrong here. This isn't typical of what I see. Let's try to get an example of that. Let's go to a star field. Clicking on the stop, and let's go back to M15. M15 is just a lot of stars.
By the way, I did look at that other object that look like it could have been a moon of, which one were we looking at, Saturn or Jupiter? And you suspected it was a star. It is. It's not in very many catalogs. It's not even in the common ones.
Uh-huh. So I'm going to M15 so I can get a star field. Basically, that's the purpose of this, is to get some kind of a star field. And I only need like 5 seconds for this. And now I'm going to come back over here and we see a definite star. You see the pattern? I mean, you don't see all these little white dots all over the place. So this is a star field that we can actually guide on. So when I click on this, it's going to pick a bright star to guide on. So what we were guiding on was a hot pixel, not a star. So there wasn't there wasn't enough bright stars in that field of view for us to do guiding. So
did you do a screen capture on that other, on
yes,
that galaxy?
I did. Yeah. So
yeah.
I had this screen.
So next time you dive into that area, I mean, you should be able to maybe visually map those stars to what you're seeing in your guide software, and it looks the same to me. You were saying that you see a lot of pixels all over.
Notice this. Notice that. So
yeah.
These are adjustments by the guide saying, hey, we've got some movement in that star, and I have to make adjustments to the mount to keep it on track. And this is what I expect to see. So that we were guiding on a hot pixel, and that's why we have these elongated stars. It wasn't really guiding. So there's not enough hot stars in this area for this image to be able to do any guiding on it. Even though it shows a bunch of stars, they weren't showing up in here. So at 120 seconds, we're seeing more stars here, but I can only go up to a maximum of what, in this guy here, 15 seconds. That's the maximum I can go to. And I've got my hot pixel map set to a maximum of 6 seconds. So if I go beyond 6 seconds, I don't have anything to subtract out the hot pixels. So now this is the level of guiding that I'm accustomed to right here. That to me is customary. So this was settling in, and this is actually doing the guiding. So now I could do a 5-minute exposure with this kind of guiding and not get any star trails.
But that's only for the current object. If you go back to M74, you'd have to do that all over again.
I would have to find something that, there would have to be a star that I could guide on, and there's no stars bright enough at 3 seconds for it to guide on. I even went up to 10 seconds and I didn't find anything at 10 seconds.
Yeah, no, I was just trying to get an idea how the software was working. So it's not like you could calibrate it one place and it's good for everywhere.
No, because the star field is what the guide scope is working on. And at the same time, when I'm taking pictures here and I'm trying to do an autofocus, again, I have to have enough stars in the image to do an autofocus. And for plate solving, I have to have even more stars for plate solving. So
it's a pretty black area of space, right?
Yeah, if there's not hardly any stars there at 6 seconds, I can't do a plate solve.
Wow.
Yeah, so now noticing this, when I zoom in on it, we're out of focus because it's been a long time since we've done an autofocus. So I would need to refocus this in order to get those into a pinpoint stars. But even out of focus, it looks pretty good at this level.
It does.
But there's no star trails. I mean, that's a round star. And if you'll notice, we have a little bit of blue fringe on one side and red fringe on the other. So that tells me that the telescope itself is not apochromatic. So an apochromatic telescope, there would not be any fringing on the star whatsoever. Now, I purchased this particular telescope. It's classified as an Edge HD, but the Edge HD simply means round stars at the corners instead of teardrops, like with other telescopes. But what it isn't, it's not an APO telescope. To get an APO telescope, instead of a $6,000 telescope, I'm moving into a $10,000 telescope. That's called a RASC, R-A-S-C. It's still made by Celestron. Or I can just throw out the reflector telescopes and get a refractor telescope. If I got a 5-inch refractor APO, which would again cost close to $10,000 for a really good one. Yeah, and it's still at the same bubble. But with a refractor telescope, then I'm limited to a very narrow range of what I can do for wide field versus narrow field. With the telescope that I've got now, I can go down to a 0.2 focal length and up to an f20. So from from an f2 to an f20, that's the range that I've got for this telescope. I don't get that with a refractor. With a refractor, I have a very narrow range that I can play with. If it starts out to be an f7 refractor, then I can go to a 14 at the most, or I can go down to a 3 or a 2 at the least, depending upon what kind of adapters I put on it. Like it's either going to be a Barlow or a focal reducer. And all that goes on the back end of the telescope. And every time I add glass to the back end of a refractor, then that takes away light from the refractor. Yeah, so this guiding right here
how many
is
magnitudes? I mean, is it? Yeah, so that just means you have to take longer exposures then?
Yeah, you take longer exposures. Typically with refractors, you're taking exposures up to 30 minutes. And the camera makes a difference too. Some cameras, you have to take very long exposures, 30 minutes to even 60 minutes, an hour long. And it depends upon the filters that you're putting onto it as well. So if I were to add filters to this telescope and say, I want to enhance the hydrogen, so I would put a hydrogen filter in there and only look at the hydrogen. So now when you use a hydrogen alpha filter to take an image, your exposure is automatically twice as long as it would be without. Because the hydrogen light is that dim. But you're only looking at the hydrogen light. You're filtering out all the other light to either end of it and just looking at hydrogen. And then when you put the red, the green, the blue, and then you try a sulfur filter, an oxygen filter, when you get down to using filters, you're going to have a 7-position filter wheel to put them all in there. And then this software here will handle it because this software has a filter wheel adjustment to it. Now for a free piece of software, this is really hard to beat. If I've got other software called Sequence Generator Pro that I paid a bundle of money for, and it has everything that this can do, but it's complex as hell. I still have not mastered it. There are still things that are happening in it that I haven't been able to figure out how to not make it happen. But this one here, I've learned everything that I needed to learn in like 3 days.
Can you connect a DSLR to this?
Yes.
Does it have to have a Digic 3 processor?
No, it'll handle different cameras. So when you look at the specs of what
because I don't have like a live view on my camera. It's pretty old.
Yeah, it doesn't matter.
Okay, good.
Doesn't matter. Digit 3, it'll handle it. It's like a Canon's, what, 50 or what is
60.
6D? Well, I've got, the one that I've got is a 6D.
30D. It's a 30D.
30D, okay. So it'll handle Canon cameras. I mean, that's one of the things that it's good for. This control right in here is for the settings. And so you have to have the interface to go with it. So there has to be an ASCOM interface to go with the camera. So if you can't find the ASCOM interface for your DSLR, then no, it won't work with it. So there has to be an ASCOM interface. All of this is on Windows, by the way. And I've been trying to get away from Windows. I just would love to get away from Windows, but I'm kind of locked in now. Anyway, guys, I'm going to have to call it a night.